Hello, good evening, everyone. Hope you all are fine. We will start the session after 2 minutes. 3 minutes, yeah. At 6:03 we would start.
Yes.
Okay, fine. Good evening, everyone. Um, so,
Greetings, sir.
yeah, hope you all are great. And so, how has been the course? I mean, we understand that this is quite a, I would say, a heavy course. Everything is packed into it. It has this coding component a lot, and not only normal coding. I mean, PDSC, we have to understand everything and then code. So we understand it's quite difficult in the time frame that we provide, but in general, how have been the course before we move into the revision session? So what's your current status? If someone wants to comment about the theoretical, I mean the technical parts, please go ahead. Okay. No one wants to say something? Fine. Great. Okay, so how we have planned this session is not only this session, that all the three revision sessions would be carried somewhat in this manner. Only the last, the Friday session, that would be a bit different. And the plan is we would solve just a mock kind of question paper for the weeks corresponding to the revision session that we are doing. Okay, and in the meantime, whenever we are solving the problem, you are free to ask any doubt, any conceptual doubt regarding those topics which is in those problems. Fine. And even by after we complete solving this, this mock paper, then again we can visit the weeks that we are discussing. little bit on some difficult concepts and maybe revise a bit more. Okay, so this has been the plan, and I would start that. But okay, before that, yeah, Mr. Bimli, you want to say something? Please.
Yeah, hi, good evening.
Good evening.
Yeah, the course has been really enriching, and I mean, there is still a lot to learn, and rather, I'll say revise also in the entire course because being first, learning this for the first time, I cannot say that. I mean, there could be many who could have mastered this subject, but then it's just a beginning for many learners like me, and. Yeah, building logic in the mind may seem to be rather easy than putting it into a kind of form of code.
Correct.
And we have been studying one particular week for 7 days, I mean throughout this 12 weeks course, and then struggling to code for that particular week, and then this 10 days of 10 weeks of content to be
Correct. Correct.
prepared for in 2 hours of coding session for someone like
No,
for
no, no.
some
Yeah, definitely.
the beginner person, that is kind of like Maji the mountain man, if I can say so.
Correct. Correct. Yeah, we agree
That
with
is
that. That's what
how
I.
I feel. But then this really, I mean, DB like in past DBMS, then there are so many interesting courses which are coming up in the diploma level, and really, I mean, very enlightening and opening someone to new ways. I mean, new paths of learning, and putting them on a kind of journey kind of thing. I would say that is how it feels right now.
Correct. Sure, sure. Yeah, thanks a lot for the inputs. Yeah, that's what I started the discussion with, right? I mean, it's super difficult in that sense to actually master the not, let alone master
See,
only.
if what I want to
Yeah,
say that it's not difficult to code certain things, but then time limit becomes a constraint, and then I mean, all the 10 weeks of content
yeah,
to revise, to practice, and then
yeah.
in
We are
a for
saying
two
from the
hours frame.
perspective of time only. Correct.
Yes,
We are
in
saying
the
from
two
the
hours of
perspective.
time, that becomes a little, not little, I mean, more than difficult task for many.
So that's why, in fact, we have not kept the OPP as one of the passing criteria, but at least a moderate kind of marks. Maybe we can, if you do it, some moderate kind of marks can be fetched, is what I believe. But anyways, we are saying that again and again. This is quite a concentrated course, and yeah, it's very difficult to cope up with it for the, at least for the first timers who are learning these things for the first time. Anyways, so today is on the theoretical discussions mostly, and if you have any doubt in code, you can also ask. Let us
Hello,
know.
sir.
Yeah, sure. Go ahead.
Sir, will there be like any coding question in exam for inter?
Not coding question, so to say, but maybe we can give a small snippet of code, and you have to, on the basis of that, choose some specific option in order to fill some part of the code. Okay, so maybe
Okay.
2 lines, line 1, line 2 we give, or a block of code which is not given as a part of the question, and you have to choose them as a part of the solution given in the options. Those things can be there, but not full code or something like that.
And end term will be 1 hour or 1.5 hour per subject.
Yeah. As far as I know, it's 1.5 hour. Okay,
Okay.
but
So the number
let
of question earlier it used to be 16.
uh,
In 1 hour it used to be 16 numbers of question. How many we could expect?
yeah. So see, the thing is, question number is not anything which is fixed. So depending upon the difficulty, we change that. So yeah, I cannot tell the question number as of now due to some reasons, but the questions would be doable in the time. That's for sure. Okay.
Thank you.
Yeah. Okay. So this is a revision session up to week 1 to 6 or 5. What was mentioned anyways?
5, week 5.
Sir,
Five,
5
right?
was mentioned.
Okay,
Up to
great.
5.
Let us see. Fine. Okay, so we would first go to that solving those questions which we were telling about, and then we would go to that some topics that you want to ask. Topic wise discussion also we would do. And while we solve those questions in the paper, you can in between you can also ask your doubt regarding that. Fine. So let me share this, and I would request all of you to join this peer deck session. Just a second, I'm sharing the screen. Yeah. So please join this session, and then I would display the questions and we would solve it. And you all can write your solutions in the meantime. So the code is RXESFL. So you go to joinpd.com and put this RXE dot, so not dot, RXESFL. Okay, I hope on your screens you would be seeing a text box. Okay. Okay, so I've also pasted the code in the comment, and now let's go to the questions. Okay, so this is one function which is given to you. And one more thing, so these questions are quite, so you also said that to discuss the quiz questions, right? So these questions which are over here, they are also very similar to the quiz questions which we had in the quiz one. Okay, so that would also be, that problem would also be solved along with it. So yeah, you all can give your responses about what would be the worst case complexity for this function. And yeah.
It's not appearing on peer deck.
Yeah, the question would not appear on peer deck. You have to see
Okay,
the
okay.
and just write your remarks. Okay, so now let's discuss it. So somebody wants to comment anything on it?
Are there only two options?
No, no, oh, sorry. Let me make it a bit smaller. Yeah. Okay, so a lot of people are in love with this complexity of n log n. So you see that everywhere, right? Most of the n log n or e log b, this form, you see that in many algorithms. Fine. Okay, so let's discuss it. See, the first part is, yeah.
So here n is either even or otherwise it will be odd. So there are two scenarios.
Yeah.
And if it is odd, then it is going in that while loop of I mean n divided by 3. So it is, if it is odd, it looks like on, and otherwise if it is even, then surely it is on. That is
Correct.
what I am thinking.
That is correct, but that's where the definition of order comes. But it means the worst case, right? It means the worst case. I don't think about what can be, what would happen in the average scenario, or what is the generalized view. My only worry is when I'm thinking about an algorithm, what can be the worst possible input that can affect my algorithm, and what would be the time at that in that case. So that is the definition of big O. So now just think from that perspective. If you said that either it could be divided by 3 or it could be a linear
No,
loop.
no. The first if condition is saying whether it is odd,
Correct.
and say otherwise it is even.
That means
So
if I have a test case in which I have an even number, what would happen? Right.
Should be ON.
yeah, so in that case it will go for on, no?
Yeah, so exactly. So that's why the answer is order of n, because that is
Yeah,
the
on
worst
P,
scenario.
I mentioned on in peer deck.
Correct. Okay, so it's order of n because the loop over here, it's a linear loop which is going to n, and as we all can see that if it's an even number, ARR, this n, the length of the array is an even number, right? Then it is a linear loop of order n, and otherwise it's a divide by 3. That means it would be log n. Okay, so either it would be log n or it would be order n, depending upon what is the length of the array. But the definition of worst case means what is the input in which it would be the worst possible scenario. See, you always have to consider the worst possible input and accordingly answer. Fine. Achha. So it's order of n. Now this is the second question, and let me just modify this question a little bit. What is the time conflict? Okay, not this one. Another question. Yeah, in the
No,
same text.
in the previous question, if it was not like n floor division 3, some other condition would have been there. And what I mean, what other condition could be put there?
Okay, so let's say I put something like I put a 2 inner loops in the while loop. While n greater than 1, let's say in case of that there is some under the if condition. Under the if condition we have 2 for loops nested.
Yes.
Done. So that would be n squared time, assuming both of them runs I1 to n, I1 to n. So in that case, both of them would be n squared time, and the else part would be only order n time. So in that case, the answer of that function would be order n squared.
So if there's no else in this, will it be log n or n log n?
Which one? If there is no
Else part, it is only n is equal to n divided by 3.
correct.
So then the complexity worst will be n log n or only log n?
What do you think?
I think should be log n only.
Log n.
Correct, log n.
But
Right.
if there will be 2 loops, then it will be n log n.
Yeah, if there would have been 2 loops, then it would be, then it can be anything. If it runs n times, then it is n square. If it runs only n by 3, I'm using, then it would be n log n, whatever. But in this case, it would be log n. Why it would be log n? Actually, it would be log base 3n numerically if you want to validate. So let's say n equal to a number, anything. It should be first of all a odd number, right? So n equal to 33. Take n equal to 33. Okay. So you divide by 3, you get 11. Then you again divide by 3, you get 3 point something, which is 3. And then you again divide by 3, you get 1. So you iterated 3 times when you took a number 33. So if you check the log base 2 value of 33, it would be more than that. It would be something around 4 point something. Log base 2 of 33. But if you do log base 3 of 33, then you get 3 as the answer. Okay, so numerically, it's always log base 3 because you're dividing by 3, and in order to reach 1, you need log base 3 steps. But asymptotic complexity we have discussed, right? So let me just shortly draw that again. So it doesn't matter when I write order of log any base x, that is simply equal to order of log x. I can totally ignore the base. Why is it so? In terms of number of comparison, in terms of actual processor execution time, it would be hugely different. But theoretically, when we analyze programs, we do not consider the base. The reason for that is asymptotic complexity do not consider constants. Now, what kind of constant? Let's bring that. We know the notion that O of 2x is equal to O of x. Right? So this is fine. This thing we know. So we would just do that over here, apply some log properties, and we would try to come up with a constant. How do we do that? We can do it simply like say log x base e. Okay, and then what we do is log a base e. So this is equal to this one. According to the properties of logarithm, this statement is just equal to that. Now, if you do that, I can also write it as order of 1 by log a base e into log x. Right? Now, base e, generally we can ignore that, right? So it's fine, log x. So this is just a constant, right? There is no variable in this part. A is a constant, right? And e is the natural long constant, 2.718. Fine. So this is a constant. So simply O will ignore that, and you can simply state that it's order of log. Fine. So divide by 3, divide by 4, divide by 2, divide by anything, it would always take order of log n. Okay, and again, just re-mentioning that. So if in this place under the condition, there would have been a function, there would have been a code snippet which took more than order of n time, maybe a nested loop, pre-nested loop, which takes n cube time. In that case, the answer would be order of n cube, because in that case, this odd part means this if part would be the worst possible scenario. So you have to pick up the worst possible scenario in this kind of branching kind of code where there are 2 or more possibilities. You need to think which one would be the worst possible scenario, and that's your answer. If the question asks you about the worst case complexity. So in this case, it was order of n. Yeah. So this question, simple question, you don't have to answer on your time. Just over here you can tell if someone wants to.
When two.
It's O(n) square.
N square. Fine. So let me just restate this problem in a different way. Okay. So let me ask you. So what would be the same question if I do insertion sort? What would happen for insertion sort?
N.
It would be O(n).
Order. Right.
Yes.
Yeah. This is a good question. And let me just modify this question a little bit. I also want you to give me the number of swap that would happen. Whatever is your answer, now you have to write it on field day. Okay, write the name of the sort, which is the solution, and along with that, try to write the number of swaps that particular sort would do in a input of size n.
So we have to answer in the same box in the.
Yeah. Just delete all those things. It's
Okay.
getting recorded. Just write in the same box. Pretty interesting answers coming up, and yeah, this is nice. This is a nice question to discuss. Okay, so let me tell you this. We are getting the correct answer very less number of times. I mean, the very few of you have given the correct answer actually. Let me see if it changes. Okay, so anyone wants to say something? This is kind of a discussion, huh? So all of you please participate because it's
It
important.
won't be merge sort certainly.
Why?
I mean,
Anything you have to state the logic that you think. Yeah.
it has the most number of swaps. It is based on swapping, right? Splitting and swapping.
So all insertion sort, quick sort, everything is based on swapping. We call this sorting as comparison based swapping sorting algorithm. So all of them would swap. You have to think about the number of swaps. So this question actually requires you to understand all the algorithms in detail. Otherwise, you would not be able to calculate the number of swaps.
There actually in merge sort and in quick sort, in the worst case scenario, there will be n swaps. While in selection sort, there will be less. There can be less than n swap.
In
In worst case, n-1 swap.
okay, in quick sort, what can be the worst case scenario? Number of swaps?
If it is, suppose we are starting in ascending order and
Okay.
everything is in descending order,
Huh?
then then I have to take a pivot and I have to arrange. Then that arrangement, that in that arrangement, so let's say there are n elements. So n-1 element I have to operate on, in which swapping will swapping can take place.
Yeah, you are on the correct path. See,
I mean, we have to break it, and then we have to swap every time. So first time it will be 2 elements. In worst case scenario, I'm talking. Then second time there will be 4 elements. Then third time it will be 8. So like that it will. I mean, log n times I have to swap in one go, just to identify where to place the pivot.
In worst case, it would not be log n actually. See, when you are in the quick short, whatever you said is exactly correct, but maybe a little bit busy. So what I want to say is, you take the worst case of quick short. You choose the pivot such that it is the one of the extremum pivot. That is either it would be the first element or it would be the last element in the list. Okay. Now, when you are swapping, right? What does the partition algorithm does? It checks, and whenever there is a smaller element, it swaps, right?
Yeah.
Now, in the worst case, you would do that swapping for all the elements, correct?
Yeah.
So for every pivot, so let's say this is my array, and this is the element, the last element is pivot or first element is pivot, whatever. And this element is actually at its correct position. This is actually, it would be the last element in its in the sorted array, right?
Yes.
So in that case, whenever partition algorithm is applied, or let's say we choose the last element and it would be placed in the first position, whatever, it's to none. So what I mean is, for the first element, in worst case, you need to swap all the elements which are present over here. I mean, one by one, you check, okay, it is smaller, swap it, smaller, swap it, smaller, swap it. You do that for how many elements? n-1.
n-1. Then we have to move pivot also.
Then you have to move the pivot also. Okay. So next time when you do, so let's say I assume that n-1 element, I mean, this pivot is actually at its correct position, right? So my new array would be this part. Now my new pivot would be, this one. Okay. Again, suppose this is again the worst case. All the cases are worst case corresponding. Okay. So now this is done. This is already placed at its proper position. So this blue part is done. Now I am at this orange part, and this is my pivot. Again, this orange part is again the worst case scenario. It is the extremum element. So how many elements? So this size is n-1, right? Because the blue part is already fixed. So now this whole size is n-1, and I only need to search over here, which is n-1 minus 1, n-2 is the second size. So I have to do n-2 swaps again in worst possible scenario. Now this would continue n-3 ... plus 1, right? And this would give you n into n plus 1, which is n by 2 number of swaps.
Yeah.
This is the summation formula, and this is your number of swaps. So even if you do not go into the so much analysis, you can just say that even by comparing directly the complexity of quicksort, that in worst case it can be order of n. Okay, and if you want to exactly, but some questions may ask what is the number of swaps. So then you have to actually think how the algorithm is processing and calculate the number of swaps. You cannot just do and say, you cannot just say that it's n square. You have to say it's n square minus n by 2. But anyways, so in quicksort we saw that the swaps are something in range of n square. Okay.
In the case with merge sort, I mean similar case.
Yeah, what is happening in merge sort? See, merge sort, again similar kind of operation is happening, but there the number of swaps is obviously lesser than the worst case of quicksort, which is n square. In merge sort, you are dividing the array into parts and then comparing the equality of arrays, right? And assuming at each level that if I have these two sub arrays, right? This is sub array which has m elements, and this is a sub array which has n elements, and I am calling merge operation on them. This is what merge sort means, right? You divide the array and then you merge. So when you merge, my assumption is these two are sorted. Both of them are sorted, correct? And how we actually assume this, because we go down to the at bottom level when it's trivially sorted, that is one element. M equal to 1, n equal to 1. Again, then when we combine, right? That is when we call the merge, then again we combine on the basis of equality comparison operator, and that's how we get it. So I'm not going into the general discussion. You all should know by now the merge algorithm, but what merge algorithm is expecting two sorted subarrays, each one is size m, another is size n, correct? And when it merges, what is the worst case number of comparison that it might do? That is one question. Can someone answer that? Comparison, worst case.
Minimum of m and n.
Sorry, can you
Sir,
repeat?
log n.
Minimum of m and n.
Minimum of m and n. So first answer would be minimum of m and n. That is one probable answer. Any other
M
answer?
plus n minus 1.
Log n one said. Another answer is n plus n. Any other answer? Okay. See, so what happens in a merge algorithm? Let's say 2, 6, 10, 1, 9. Yeah. Fine. So these two are my sorted subarrays. In this case, okay, let's take one more element over here. No, let's take over here 11. Okay, so this array has 4 elements, and obviously it's sorted, and this has 3 elements. Obviously, again it is sorted. I call the merge algorithm. How it would work? Okay, so first comparison would be 2 and 1. 2 and 1, and here I am writing the array, the sorted sequence. Okay, so 2 and 1 is the first comparison. 1 is smaller, so I would put 1 in this place. Okay, what is the second comparison that would happen?
2 and 9.
Correct. Second comparison is 2 and 9. So you compare 2 with 9 now. So I see that 2 is smaller, so I put 2 over here and cross it. Correct. Third comparison.
6, 9.
Correct. So you see 6, 9, 6 is smaller, put 6 crossed, then 10, 9. Obviously 9 is smaller, put 9, crossed, and then 10, 12. 10 is smaller, put 10 over here, cross it. Final 11, 12, put 11 over here, cross it. Last one is 12. Okay. So how many comparisons did we do? If you check that, the maximum possible scenario, in this case, it would be something lesser than the answer value, answer I'm telling. But in worst case scenario, what you are doing is you are comparing each element of over here to one element in the right array. If it is the least element, then you simply place it. And while you compare one, let's say you compare 1 and 2, right? So since these two sub-arrays are sorted, you do not have to compare 2 with 9, because you know if it is lesser than 1, okay, sorry, if 1 is lesser than 2, then it is the least possible value in the sub-array, because all other value after 1 is obviously larger than 1, because I know my sub-array is sorted ascending order, in ascending order. So you did not have to compare 2 with 9 and 2 with 12, and that is what we gain in the merge algorithm. Otherwise, it would be n square. But here we are actually comparing one element with another, and either one of them, right? So let me restate it. So what I want to say is, in every comparison, at least one of the element or number, whatever you say, would be placed, right? I can take one decision that for every comparison, I can at least correctly place one of the numbers, right? I do not have to do more than one comparison in order to place a single number. So every comparison would place one number in its correct position. So if that is the case, and one more last observation is that the last number which is left, right? So in this case it was 12. I do not have to compare that with anything, because that's the only last number left, and we can place it directly. Okay, so 2 points. Just think of this logic. Since these two sub-arrays are sorted, every comparison between two numbers, every comparison between two numbers is giving me the facility to place at least one number in the correct sequence, right? So every comparison would place at least one number in the correct sequence. So what is the worst case possibility till you exhaust the whole sub-array? I mean, the sum of the two sub-arrays. It is m plus n minus 1.
But
Right?
sir, if there will be, let's say there are 10 elements, one side.
Just a second. So it is m plus n in order to, because if every comparison is giving me one element, m plus n number of comparison I would give me the whole list. But it is one last comparison I did not do, because it would be m plus n minus 1. Because this last number I do not have to compare with anything. Yeah, now you say what you are saying.
So let's assume, sir, in left hand side I have 10 elements, on right hand side I have only 5 elements.
Fine.
Then the comparison will only happen for 10 times.
I am telling worst case, right? We are not going for best case possible scenarios. I am saying the worst case number of comparison. What is the worst case? Okay. So if you have even one element and let's say 200 elements, so there would be just one single comparison. The first element of this list with the first element of this list. That's it. After in one comparison, you would place, let's say we place this over here, and then all the 200 elements would come after that. Anyways, so that is the best possible scenario, but we are talking about the worst possible scenario. So you do so many comparison, and accordingly you can understand that whenever we are placing it over here, in the other part of the array, we are actually doing a swap. In the while loop of merge function, if you check, we did a swap. Okay, and obviously, so if I just want to make it simpler and convert everything in terms of a single variable which is n, so again it would be some linear, and this might go on for log n step, right? We know merge sort every time divides the array into two equal parts, and that's why it would always be log n. It would not be the worst case kind of thing like quick sort. It would be log n. So we have around n log n. It's not exactly n log n, but it's order of n log n number of comparison, just according to the our complexity. Fine. So it's order of n log n. Quick sort is order of n square. Which ones are left? Insertion sort, selection sort. So let's discuss insertion sort. Anybody wants to say how many comparison would be done in insertion sort? Sorry, not comparison, swaps.
Sir, in worst case, suppose it's the array is in descending order,
Okay.
and if so the first element sir, insertion sort, I have to do, suppose there is 4 elements in descending order, 4 3 2 1, like that. And in insertion sort, suppose for the last element 1, I have to swap 3 times, at the place of 2, then at the place of 3, at the place of 4, and I have to move the 4 3 2 accordingly. So I have to do 3 plus 3, 6 swaps. So this is the worst case for insertion sort.
Correct. So can you generalize it? Let's say I have 10 elements. So how many swaps I would need?
So it's n square. No, in
Order of n square, correct. But okay, so let's discuss the exact value. So as you just said, so if we have, let's say, the sequence 10 9 8 7 6. Correct answer, by the way. So let's say 10 9 8 7 6. Okay, now we are starting from here, insertion sort. We check 9 with 10, and obviously 9 is smaller than 10. So we would do a swap 9 10, and then dot dot dot, whatever is it. After that, in the next step, what would happen? We would see 8, right? So 8 is over here, and I check 8 with 10. I see that 8 and 10 must be swapped. So I did another swap. After that, we check 8 with 9, and we see, okay, again I have to do another swap. So 8 comes over here, 9 comes over here, 10 comes over here. So for 9, we did one swap, right? For 9, we did one swap. What was the swap? 9 and 10. For 8, we did 2 swaps. What were the swaps? 8 with 10 at first, and then 8 with 9.
Sir, isn't it for 8 also we'll swap it one time, but we will compare it 2 times?
Yeah, we are comparing. Obviously, every swap is a comparison, right? You are not swapping. I mean, what would be the statement? If whatever aj is less than aj minus 1, then you swap.
What he is saying that instead of making a swap with 10 and then again with 9, but swap is like replacing two values with
Replacing.
their respective place. So if we swap directly 8 with 9, that cannot happen. Why? Because there is no placeholder before 9. So if we swap again 8 with 9, then again 9 has to be swapped with 10. So there will be 2 times swaps at least.
So this is an array kind of thing, right? You cannot array or I mean list, whatever you want to say. You do not have a space before that, so you have to place it. So normally insertion sort, we actually take a number and compare it with. So if this is my array, and this is the current iteration that I am doing on insertion sort, right? So sorry. Yeah, this is my element which I am comparing. I would compare. So this part would be my sorted part, and this would be my unsorted part, right? And the current element is the one which I'm trying to put into the sorted part. What I would do, I would compare this element with all the elements sequentially, with this one, with this one, with this one, and accordingly, whichever is its correct place, I would place the element over there. Assuming this is the correct place, I place it over there. Fine. So this is how the insertion sort works, because we are inserting the element into the sorted part on your left hand side. So anyway, so for 8 we did 2 swaps, 10 and 9. Now if we proceed further, we would see for 7, the third number, we would do 3 swaps. And what would be the sequence? First would be 7 and 10. Then would be 7 with 9. And then 7 with 8. So you see the pattern over here, that for every element, if it is sorted in the opposite order, as one of you said correctly. So in that case, I would have to make the swaps n minus 1 times for the nth element, n minus 2 times for the n minus 1th element, like that. So for 9, I have to swap 1 time. For 8, I have to swap 2 times, like that. right? So for n, I have to swap n minus 1. I mean, for n elements, if there are n elements, right? For the nth element, I have to swap n minus 1 times. For the n minus 1th element, I have to swap n minus 2 times accordingly. So my swap total number of swaps would be n minus 1 plus n minus 2 plus dot 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 n minus 3 plus 1. So which is again n square minus n by 2. Fine. So this is actually the exact number of swaps. And again, if you just convert it in terms of order, it is n square. Okay, so mostly you would see the algorithmic complexity and the number of swaps is kind of same in most of the algorithms, but if the question asks you to exactly state the number of swaps, then you have to actually think and calculate the number of swaps, right? You have to tell n square minus n by 2 and not only n square. Fine. So insertion sort took order of, let's say, in n square, it took in n log n, quick sort took n square, selection sort. Anybody wants to answer?
n minus 1 time in worst case.
Correct. Because how selection sort works. So let's take the same example which we took over here. Right? This 10, 9, 8, 7, 6 array. How does selection sort works? Its simple logic is you search through the whole array, right? You search through the whole array, pick the element which is the smallest element and place it at the first position. Place it means swap it, right? So if this is my array and this is the worst case for insertion sort, right? Let's apply selection sort and see how many swaps are there. So I check at first 10. Is 10 the smallest element? I don't know. I would proceed and then find. So let's compare 10 and 9. Which one is smallest? 9 is smallest. Okay. So I do not swap them. In insertion sort, we were swapping. Here we do not swap. I just want to find the minimum element. That's it. Okay. So when we find minimum element, what happens? We simply compare. We do not swap unless and until we complete the whole array. So I find 10 and 9. 9 is the smallest element. So I in a variable where I maintain the index of the current smallest element. In that index, I modify it from 0 to 1. Why? Because 9 is located on 1 and 9 is currently my smallest seen element. So 9 is smallest. After that, the next comparison would be 9 and 8. Right? So I do the next comparison 9 and 8 and I see 8 is the smallest one. So I again change my index of the smallest element to be 2 because 8 is located at 2 index. Finally, the next again one comparison with 8 and 7 and accordingly we would modify and then 7 and 6 and accordingly we would modify. Fine. At the end, we see that we have reached the end of the loop, I mean the array, and as of now 6 is the smallest element that I got. Understand this thing, we are not swapping, we are only comparing. In insertion sort, we were actually doing the swaps after comparing. Here we are only comparing. Now, when I found that 6 is the smallest element, then I would do the swap and that swap would happen only one time. With 10, this swap would happen. 10 and 6 would be swapped. So 6 is placed over here, 9, 8, 7 and then 10. Now 6 is sorted, right? 6 is fine. So we keep 6 separately and we apply the same algorithm on this part, 9, 8, 7, 6. Again, find the minimum element on 9, 8, 7, 6 and whichever is the minimum, you swap it and place it in the place of 9. And then again, you do it on this part and find the minimum element and place it in place of 8. Again, on this part, find the minimum element among these two and place it in place of 7. So essentially, you are doing the comparison every time. N minus 1 plus n minus 2 plus n minus 3 dot 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 1. So number of comparisons in selection sort, number of comparisons is n square. Okay, or n square minus n by 2, order of n square. Selection sort, worst case scenario, right? Comparison is n square. But I am doing the swap only once after iterating in order to find the correct position, right? After completely iterating the leftover part of the array. So for every number, I am just swapping once. And the last number would anyway be placed, will be placed, right, at its position. So ultimately we get n minus 1, as one of you said correctly. the number of swaps is n minus 1. But the number of comparison is order of n square. And that's why the complexity of selection sort is order of n square, worst case is n square. But number of swaps is order of n. So this is very important. Up till now, whatever we have seen, most of the algorithms had similar kind of complexity as well as the number of swaps. But selection sort we get comparison or complexity is n square, but swaps is only order of n. Fine. So your answer is selection sort because it takes order of n time. All other takes time which is more than order of n. Sorry, not time, number of swaps. Any doubt in this?
No, sir.
Fine.
No, but when we are saying swap, that is actually involving some operation.
Yeah, that
But
actually swapping.
Complexity is also based on some operation.
Complexity is based on comparisons. Complexity is based on all operations. All operations include swapping plus comparison. Swapping also takes order of one time. Each swap takes order one time. Each comparison takes order one time. Both of them takes order of one time. But time complexity is based on swaps plus comparisons. Okay. Now in selection sort, the comparison is doing the heavy lifting. It is taking n square time, n square number of comparisons. That's why the complexity is also n square. But the swaps is order of n. So that's why we consider the greatest value, right? So we consider the comparison sort. Okay. Fine.
Sir,
Huh.
if it is asked about a number of comparison performed, then how what can be done, sir?
How for selection sort we just discussed, right? N minus 1.
Yes, sir.
Yeah. How, you want to ask how we will solve it?
Yes, no, actually, I mean, that if suppose that if for a specific question, like if the array are already sorted,
Okay.
then what can be the which algorithm performs the least comparisons between numbers?
If the array is sorted in the proper order only, right?
Yes, sir. In ascending order.
Yeah. So in that case, insertion sort would give you order of n, right?
Yes, sir.
Insertion sort would do it in order of n time. Best case complexity of insertion sort order n. But okay, so now this is interesting. What would selection sort do? What would be the complexity of selection sort in best case?
Sir, I think n square.
Correct. So that's the problem.
For any case. For any case.
There
For
is
any
no
case.
change.
Yes. So selection sort. So now let me ask this question. We came up with an interesting observation. So by considering this factor, now when you understand all these factors, you will be able to decide which algorithm to use. There is no better algorithm, or sorry, there is no best algorithm. So in a system where swapping is more costly, right? Let's say the system is designed in such a manner that swapping is a difficult operation to do. So in those kind of systems, and when you are actually considering the performance of a system, you do not go for asymptotic complexity. You actually go for number of clocks or number of nanoseconds taken to do the operations. So in that case, we would have to be very precise and exact. Correct. So order of, and there is no question of order. There is question of order in nanoseconds. Okay, so you have to be very precise. So in those kind of scenario where there is a swap happening and that swap is taking more time, in those systems it is better to avoid selection sort. It's better to take selection sort because selection sort has the least number of swaps happen. Okay, even though its complexity is order of n square, but again, if you are not working on a huge set of data and in your system the swapping is a heavy operation to do, you should go for selection sort. On the other hand, if you have a system where you would be working on a huge set of data, correct, and maybe you should think of something like merge sort, and that would be better because it would always give you in log n time. Okay, or you can also use the median of median and then apply good shot. But anyway, so prefer any n log n algorithm. So these kind of things are there. Insertion sort, again, if it's already a sorted array, insertion sort is the best case, which gives you a linear time. Selection sort always gives you order of n square, irrespective of the the type of the array, the input array. But the swaps in selection sorts are minimum. Sort is minimum. Direct question, you don't have to even discuss it if you have any problem. So basically, the merge sort recurrence relation is asked over here. So if you have an array, you simply divide it into two parts in the merge sort. So it's Tn by 2, and you are dividing into two parts, so it's obviously 2 into Tn by 2, right? And after that, you call the merge algorithm on the subparts in the divided parts of the array which you just divided. So that takes a merge algorithm takes. We just discussed how many comparison, n plus n minus 1, right? In worst case, it would take n plus n minus 1. Now, if I simply make it in terms of a single variable, so the answer is exactly it is n plus n minus 1 comparisons it could do. But assuming that we divided the array into exactly same number of elements, so both would be n plus n minus 1, which is 2n minus 1, which is in terms of order a to n. Okay, so this is for the merge algorithm. So merge algorithm would take order n time. So this is the factor over here, the order of n time. Okay, and 2n by 2 is the number of we are dividing the array into two parts, and there are two parts, therefore it's two halves, and there are two such halves, so therefore 2n by 2. And we know the complexity, obviously to solve this recurrence, the answer is n log n, order of n log n. And yeah, so that's why this is the correct. Okay, so let's go to the next question. So this is partition algorithm. So this is the array which is given 8621457. Just apply partition algorithm on it and tell what is the answer. I mean, which of the following array you get as the answer?
So can you scroll little up?
There is nothing below it. This much. Oh, up you said, right? Just a second.
Yeah.
You all may write on the same text box only.
It will be last element will be 8, then 7, and from beginning to it will be sorted, and but till up to the penultimate item, last element will be 7 only.
No, sorry. After the partition algorithm finishes, what should be the sequence?
Until sorting. Sorry.
So here pivot is the last element, right?
It is mentioned, right? Putting the just a second. What will you which uses the last element of the list as the
Okay.
Okay. So anyone wants to say what should be the sequence?
One second, please.
Huh.
I mean, it is oscillating between the ith element and the last element, and after the for loop, 8 will go towards the last. So 6 will come in the beginning. So 6 between C and D, it looks like I'm not been able to finish complete iteration.
Okay. Okay. No, it is okay. So let us do that. Okay. So a quick shot. This partition algorithm, you can solve it in either of the two ways. The concept is exactly similar. I mean, just the Corman book, if that's the reference book, right? So if some of you have seen through the Corman book, it would be a different approach, and if you see the lectures, it would be a bit different. But they are just the same thing, and you can approach in either of the possible ways. No problem. The answer is obviously the same. The process is also same. Just Sir's approach is we do the swapping before, and the Corman's approach is after we find the thing, then we do the swap. Anyways, just follow along. You would get what we want to do. So if the first state of the array is 8, 6, 2, 1, 4, 5, and 7. And 7 is my pivot element. Okay. So first step that we do is we would check. You can also do it in this fashion. Just follow along what happens. So at first we would do is, what is 8? I would compare the first element with 7. If that element is smaller, then I would do the swap. If it is not, I would not do the swap. So 8 is not smaller than 7, right? Because if it is smaller, then I have to pick it and put it on the left hand side, right? So 8 is not smaller than 7. So keep 8 at its place. So after that, in the next iteration, 8, 6, 2, 1, sorry, not this one. So my first iteration is done, and it is 8, 6, 2, 1, 4, 5, 7. What was the comparison done as a part of this iteration? The comparison was 8 with 7. Okay. Now let's do the second case. So I'm writing it over here. 8 and 7 were compared. After that, we would do the second case where 6 has to be compared with 7. Now, with the pivot, you are comparing the next number, which is 6. So compare 6 with 7, you see, okay, 6 is lesser than 7. Right? 6 is lesser than 7. And I have to swap. Now, from which element I must do the swap? So you would maintain 2 pointers, right? I and j, there are 2 pointers that you maintain. So you maintain a pointer I over here in the first element. And j would simply traverse through the whole array. So currently j is at 6 because that's the number you are considering. Okay. So you check a of j, which is 6, is lesser than 7 or not. Yeah, it is lesser than 7. Whenever it is lesser than 7, then you would swap. So I would swap 8 and 6. I would put 6 over here, then 8. Okay. Fine. So my I is over here. My j would move to now 2 because I have already compared 6 and 8. So j moves to 2, 1, 4, 5, 7. Okay. Now next comparison j. J is moving forward through the loop. So j would compare 2 with 7. Next thing. So I would compare all these j values with the 7 up to 5, right? At the end. And whenever I am finding a smaller value, I would swap that smaller value with the that the position of I in that moment. So just see what happens. So I am here at 2. So I'm comparing 2 with 7. Done. Now 2 is again smaller than 7. So I must move it towards the left side. So how I will do it? I will simply swap again. Move I one ahead and swap it. So that's the convention that Corman followed. So this was asked by a student that there is a different convention in the book. That's why I'm discussing it in this manner. You can also do it in the manner which is discussed in the lecture. Okay, I'm just proving that both of them would give you the correct result. So what is the thing? When you find the smaller number, you simply increment I by 1 and then do the swap, because you have already swapped 6, right? You placed 6 in this place, right? And if you again do swap with 6, that's not something that we want. That's first time you have swapped, and that's how you put 6 in this place. 6 and 8 you give the swap, right? So you will move I over here. So whenever you find the smaller value, make +1 and do the swap. Okay. So I did +1, 6. Sorry, I was increased by 1 unit and it moved from 6 to 8. Now I would swap I and j. Okay. So the mantra is find the number which is smaller than the pivot. If you find the number, add 1 with I, do swap I and j. That's the thing. Add I by 1, swap I and j. Okay. And here I find 2, which is lesser. So I increased I from 6 to 8 and I will do the swap. So 6, 2, 8, 1, 4, 5, 7. Okay. So where is I right now? I is in place of 2 and J was over here. So J is in place to move over here. Okay. Now I check 1 with 7. 1 is again smaller. Same, apply the same thing. Increase I by 1, swap I and j. So I'm writing over here 6, 2 was there. Now I must be increased to point towards 8. So I'm increasing I by 1, right? Over here I, and I would swap I and j. So if I swap it, 8 would become 1. And after that 8 would be here. And j is obviously was in this place, so j would move to the next number, which is 2. Again check 4 with 7. Is 4 lesser than 7? Correct. Since 4 is lesser than 7, increase I by 1 and then swap I and j. So I is moved over here. Swap I and j. 6, 2, 1, 4, 4, 8, 5, 7. Okay. J is at 5 now. And I is at 8. Sorry, I is at 4 now. Because I am not increasing after the swap. Before the swap, I am increasing I and then swap. So ij, 5 is lesser than 7 again. Yes, it is lesser. So simply again same step, increase I by 1 and then swap I. So I is increased from 4 to 8 and then I am swapping I and j. So that would give me 6, 2, 1, 4, 5, 3, 7. Right. So this is my up to 5 we have sorted. Now after that, what would happen? I would simply be putting the pivot element in its appropriate position, right? We have this last line. So when you finally put the pivot at its correct position, so you simply put 7 at the I plus 1 value, right? So you put 6. This is your answer. And again, so this has been, I just did it in this manner because it's the way Corman has done it. And I mean, one mail was there which was telling that a quickshot is working in this manner, how it is happening. So this is how it happens. Nothing. And what happens in our approach, which we have done in the course, is just that we increase both I and j together and then you. So here we increase. I mean, after finding the minimum, and there, and in our case, we increase it before and then we do this. That's it. So simple partition algorithm, quick short, revise that, and I hope you would be able to answer.
Sir, for both the mechanism, the answer will be
Same. Yeah.
Okay.
Okay, so this is again on the complexity. Okay, I'm just trying to solve it. I would not ask this one because the plans are also there. Okay, fine. Can someone tell me, by the way, what would be F1? Can you solve it? Is it the most
Sir,
simplified?
n. It will be n.
Correct. So it is n. Why? Because 2 to the power log 2. In fact, any a to the power log a x, right? It is simply equal to x. Fine. Why it is so? According to the logarithmic property, if you are raising a to the power log, that means you are at the base is a, right? The base is a, right? So that means simply you are, I mean, to the power and log are opposite things. Understand it in this manner. If you don't know the properties, yeah, I mean, to the power and log are two opposite things. So if you are raising to the power and then you are keeping the base value that same constant in logarithm, then that just cancels each other. So you get the value x. Okay, so see here 2 to the power log base 2 is there, so that simply gets cancelled and you get order of n. I mean n as the function. All others are same, n square n log n. There is no simplification possible. So these are the functions, and obviously you can understand log n is the smallest one, right? After that we have n. So f4 would be the smallest one, then f1, then I have n log n, f3, and finally n square is the last one. So f4, f1, this is the correct one. Now my question is, if we consider the case, let's say, now which one is greater in this case?
N log n is greater.
Can you, I mean, how would you approach it? Let's say.
Okay, so the first one is log n square, log n times log n, and second one is n log n. So log n, I mean the right hand side of both the
Comparable, same.
is
Correct.
same. Left hand side, if we compare, log n is smaller than n.
Sure. Correct. Okay. And if we just change it somehow, let's say, by the way, can you tell me what would be the answer of this thing? This is nice. Not n log n. Let's go for root n. Or no, not also root n. Let's say root n only. Now what would be the answer?
The root n is smaller than log 10 and of log 10.
Sorry, I could not hear you.
Root n is smaller.
Root n is smaller?
Yeah.
Log square n will grow slowly much more slowly than root n.
The root n is larger in that case.
Yes.
So we got two answers. One is smaller, another is larger. Now give me your logic. How you actually came up with this conclusion? Just by seeing the function?
No, sir.
Or by substituting value?
If we take 4 and if we assume the base is 2, then log square n will be 4. However, the root n will be 2.
If we take n equal to 4, root n will be 2, and if we take over there 4, right? And
Yeah.
assume that this is base 2. Just assume that for our calculation.
Yeah, then it will be 4.
Okay, so log 4 base 2 would be 2 to the 4, and here it would be 2. So this is 4. This is 2 when n equal to 4. So root n is smaller. So that's what I said, that you are putting values and checking, right? That just check which one is smaller. So this is not the correct way to do it, because now we will go to the definition of asymptotic complexity, and let us see what the formal definition said, and why those things are important, even though we kind of ignore all those things sometimes. So what was the definition of big O notation? What was the definition of that? The definition was, we would say a function f of n equal to order
Beyond
of,
n0.
correct, correct, exactly. That's the point that we were. That fn equal to order of g of n. We are saying that means that f of n is lesser than some constant into g of n for all n greater than n0 and c greater than. This was the formal definition of order, right? So when we mentioned these two conditions, that c must be greater than 0 and for all n greater than n0, or a constant, a number, right? N greater than n. So according to the logic, I can write log square n, right? According to the not logic, according to this value which we got 4n. According to value, root n is smaller, correct? If root n is smaller, I should write root n equal to order of, I can write log square base 2n, right? But the problem is, if I take sufficiently large values, right, very, very large values, then I would see that root n is actually giving me larger value. So let us take an example, try to think of a very large value and see what's happening. So I also don't know, let's take a value 2 to the power 10. Okay. So if we put 2 to the power 10 in case of root n, it would give to 2 to the power 5. Okay. And here what I'm getting, if I put 2 to the power 10, I'm getting 10 square. So still it is greater, it is smaller. It is 32, right? 2 to the power 5 means 30. And here it means 100. Right? It is smaller. But now let's take even larger number and let's see what happens. 2 to the power, let's say 30. So I would get 2 to the power 15 in case of root n, and log square n, what it would give me, 2 to the power 30 if I take, so 30 square. What is 30 square? 900. Right? What is 2 to the power 15? 2 to the power 10
very high number.
is 1024.
Into 5.2.
Right? So 2048. After that, you multiply 4096 or something like that, I think.
Like that.
4096, whatever, doesn't matter. So what I mean is, when you took the value of 2 to the power 30 and put it in place of root n, you see that root n is a much larger value and the log square n is giving a smaller value. Correct? So, okay, what did I say? Did I say it correctly? 2 to the power 30, right? 2 to the power 15. Yeah, correct. So log square n is giving me 900 and root n is giving me 2 to the power 15. So that is a very large value and huge difference. Correct. So that is the problem. See, if you put values, I can, what does this mean? Why we came to this definition? It was greater than n naught. So I can simply state that this value n equal to 4, right? My n naught is here greater than 4. My n naught over here is greater than 4. And that's why I cannot state just on the basis of this observation that n equal to 4, my here it's 4 and here it is 2. I cannot say that root n is smaller. Or I cannot say that root n is equal to log square n. This I cannot say, because in this statement my counter logic is this part, right? I am just saying that it must be greater than n naught and my n naught is greater than 4. You are simply putting n equal to 4 and checking. No, you cannot do that, because I have stated the definition only validates when is valid when you are taking a value which is greater than some constant n naught, and n naught is also greater than 0. Fine. Here n naught is greater than 4. That's it. And your logic is false. Even I would say n naught is greater than 2 to the power 10. I would say n naught is greater than 2 to the power 10. Right. So just at the boundary, right? We tested with 2 to the power 10. We saw that root n is smaller. We tested with 2 to the power 15. 2 to the power 30. We got that. Yeah. Now root n is giving me larger value. So I would simply state whatever is the boundary, right? There must be a boundary between 2 to the power 10 and 2 to the power 30. From where root n is actually giving larger value than log square n. So I would simply state n naught is greater than that value. Assume over here, let's be very simple with it, and simply if I state that I apply the condition definition of order, but this is the condition. Totally valid. Asymptotic complexity only says it should be greater than 0. Yeah, greater than 0. So why we do that? We do that because our motive is for very large input. What would happen in our algorithm? That is the very motive of this statement, that n greater than n naught. Right? You simply put small value, then on the basis of that you simply plug in the value and check what is the answer, and you decide that this algorithm is good. Might not be the case. For larger value, the function may be, the growth function may be totally different. It may show, I mean, you are not able to observe that feature, but when you put very large value, you would see it. So that way, substituting value and checking the growth rate is not a good way to do it. But most of the time, we have been doing that as a part of this course, and we have not discussed very difficult to compare functions. But if you have some this kind of functions, or maybe it is even still easier. There are functions which we can discuss which is very difficult to compare, right? So there, just for your knowledge, I am saying we have discussed it in one session also. I am just stating it briefly. You might not need it directly for the exam, since this is not a part of the syllabus. But obviously, you can be sure about your answer. If you feel confused about any complexity question, if you know this process, you would be very confident about your answer. You don't have to be confused. And yeah, I would just briefly mention that if anyone wants to understand that in detail, you can see that session of complexity where we have discussed. So what you would do is, it requires a basic knowledge of differentiation. You all have heard about the L'Hopital's rule in limit and continuity, I hope. So what you do is basically you take n to be very large, right? So I take n to be towards infinity. Okay. And you choose these two functions which are given to you, put one in numerator, put another in denominator, anything. So let's say in this case, I put root n in over here, and let's say I put log square n over here. There is no bound. You can put anything. Only the interpretation of your answer changes in the case if you just swap the numerator and denominator. Okay. Now, if you put the value n equal to infinity in both the places, obviously root infinity is infinity and log square infinity is again infinity. So we get a infinity by infinity form, and this is actually the condition to apply. L'Hopital's rule, or some of you might say L'Hopital's rule, whatever. So, by the way, this is there, right? I mean, this rule in calculus you must have done that.
Yes, sir.
Yes, sir. We did it.
Correct. So you simply do that. This is the infinity by infinity or 0 by 0 condition. You apply the root n, differentiation of root n. So if you do, it would be half, right? And n to the power minus half, so root n. Fine. And log square n is, I would do again a 2 and log n, and then 1 log n is there, so that would be 1 by n, so n. Fine. And then I would cut this root n with this root n. So it's root n divided by log n. So again I put infinity, still I got infinity by infinity. Right. So again apply. Okay. And then log n's differentiation I would do, it would be 1 by n. So again we go here. and then that I would get root n. So I get root n by here 2 was there and another 2 was there, so 2 to the power 3. So limit n tends to infinity, root n by 8. This is the the solution for this one. And now if I put infinity, what I get? I get root infinity, which is infinity, right? But see, it is infinity by 8, which is infinity. I have actually tried managed to eliminate the infinity in the denominator, right? So if this is infinity by infinity or 0 by 0, that is an indeterminate form. But if I have only infinity at the top, or only 0 at the top, or only infinity at the bottom, or only 0 at the bottom, either of these 4 cases, then those are not indeterminate cases. So if I have something x by infinity, x by 0, infinity by x, infinity by 0. Sorry, not 0 by x. Right? So what are these values? This is equal to 0. This is equal to infinity. This is equal to infinity. This is equal to x. 0. I hope this must be clear. All these things should have been clear. I don't know. These things are there, right, in maths? I mean, I'm
Yes, sir.
asking. Okay.
Yes, yes.
Fine. So you get the result, right? So these are not indeterminate forms. So this is not an indeterminate form. So you get the answer as infinity. Now, obviously, as a result of this process, you would either get 0 as the answer or infinity as the answer. Because at the end of the day, you would put n equal to infinity. And if your numerator expression has n and your denominator has a constant, then you would get the result as infinity. Otherwise, just if I would have chosen these two functions in the opposite manner and put the denominator in place of numerator and vice versa, then I would just end up with something 8 by root n in this case, right? And that place, when I substitute n, I would do 8 by infinity and that would give me 0. Only my functions were actually in the opposite denominations, correct? So either you would get 0 or infinity, either of these two you would get answer as a result of this process. And then you have to just do this little observation. And if someone is blindly copy pasting, he would make this error. And that is the observation. The observation is you got infinity when you put root n at the top. Correct? So that means infinity is a larger value, right? In fractions, when we divide by a numerator which is smaller than when we divide by a denominator which is smaller than the numerator, we get values greater than 1. Correct. So here also you apply the same notion, just scaled up to infinity. You are getting a positive infinity value. That means your numerator is greater than the denominator. If you would have gotten 0 or nearly 0, that means your denominator is actually greater than your numerator, because in that case you would get a lesser than 1 value, right? And in case of infinity, it would be tends to 0, that is it's equal to, we are assuming it is 0. Fine. So depending upon the result that you get, if you get infinity, that means your numerator was larger. If you get 0, that means your denominator is larger. So in this case, we got infinity, and that's why our numerator is larger, and that's actually the correct answer. Your root n is actually large, right? And that's why I can write that log of square n is equal to order of root. Fine. So this is the, analytically the correct way to solve these asymptotic complexity questions. But you have to have this differentiation knowledge and all those things. So even if it is not required directly for the course, but you can be very sure of your answer in the quiz or interview. Fine.
No, sorry, I missed that part. Why did we write log square n is order of root n?
Because root n is larger, right? We are sure of that because we got infinity, and infinity means
yes. So root n. Oh, okay. I mean, we are saying that root n is a larger function, so we can say that log square n is order of root over n.
Root over n.
But between these two, log square n is a, I mean, smaller function.
Smaller function, exactly. I mean, order of n is just that, right? So if this is my graph, let's say log square n, I mean, I'm just arbitrarily drawing the graph. Log square n is something like this, right? I can always say that root n is, maybe it is smaller over here, but after that it goes. Root n is not this graph, it should be a parabolic, opposite way parabolic graph, right? But anyways, the just the one side of the parabolic. Anyways, I'm just stating it. So over here, you see, oh no, just a minute. It's actually not like this. So the root n is actually smaller in this one, then after that it goes. Okay, so this is my log square n, this is my root n. So this is my n naught, which let's say I took 2 to the power 30. Okay, so if you see before this n naught, root n was smaller than log square n over here in this region. That's what we observed. Okay, but after that, after crossing this some threshold value, for set side we took it to the 30, but it's actually the least value where it is crossing that threshold, right? So at that point, after that point, it's getting, I mean, it's increasing. That root n is more than log square. Now, this is actually your definition of order of n. So that's why we can, any function which is bounding, right? It is bounding, it is at the top. It is at the top and it is covering log square n. That's why I can write this statement. Fine. Okay, so let's go to the next one. So this just if you have 2 pointers, fine. I'm just stating this. Please listen to it. You have 2 pointers, one head pointer and tail pointer in the linked list. Over here you can see the head pointer and one tail pointer. And this is a singly linked list, right? Pointing like this. So what would be the time taken to do all these operations? Yeah, if someone wants, please go ahead and tell the correct option.
So the insertion and insertion in the beginning and like at the end, it will be almost the same, right? Like I think it is for one insertion in the
just
beginning.
assume that you have these 2 head and tail pointers. Now you think of that. Which option is correct? At first tell the option, then we will discuss one by one.
Maybe option C.
Option C. So insertion of the new node at the front takes order 1. That is fine. Okay. You are simply, you have the head pointer. You inserted and took a new node. Just assign the head value to its next. Right. So what would be the steps that if you do the insert? Right. You would take a new node. You would do new node arrow next equal to head.
All look like operation order 1 only.
And
Right.
then you write head equal to new. That's it. So that is order 1. No issues. After that, what is the next option? C. 2 option. Second operation takes n time. Second
Yes.
operation is insertion of the new node at the end of the linked list. Right? Why is it taking n time? You have the tail pointer, right?
Yes.
Still, why you think it would take n time? You are already having the tail pointer. Just go to the tail and insert.
But deletion will take linear time
Sir,
because we don't have a pointer
Sir.
to the immediately preceding.
Sorry, I did not get. What are you saying?
But if you want to delete from the end, we would need linear time because we don't have a pointer to the one before the tail.
Not delete, not delete. I am taking the second operation, the insertion of new node at the end of the linked list. How
Sorry.
much time?
Sir,
We'll
if
take
sir,
one
if we have the
of
tail
one.
end, then it's units of constant.
Sorry,
But
sir, can you repeat?
sir, according to the question, if we have given the tail end, then I think it will take of constant time.
Correct. Tail is there. That's what
Yes.
I'm
Tail is
saying.
there. Sir, but if it's not there, it has to iterate over the entire list,
That
then
is
get
different.
that is different. But yes, that I missed that part in this
you
question.
have to be very
We have
careful
given
with
tail end.
whatever is given in the data. Huh? Very
Yes,
careful
sir.
with that.
Okay,
Okay.
sir.
So you get, since tail is there, you simply put the tail and use that to just insert. It's just like inserting in the start. If you have the tail pointer, inserting in the end is just like inserting in the start. So you take the node, and then what you do is simply tail dot next equal to the node, right? So if this is the insertion at the top, operation 1, operation 2 would be tail dot next equal to new node. And then what you do is you simply move the tail, right? So you write tail equal to new node. That's it. So second operation also order of 1, both of them order of 1 time. Deletion of the first node of the linked list. Now if you want to delete the first node, what could you do? Head, right? You want to delete head. The only thing you would do is head equal to
Yes,
head
sir.
dot next.
Yes.
Fine. So no issues with that as well. So that is also order of 1. Deletion of the last node of the linked list. How much time it would take? We have the tail pointer. Keep that in mind.
To take n.
Why? We have the tail, right?
We don't have the one for the thing before it, right?
Correct. So in order to delete, we must, what should we do? If this is the node which is just before the last node, assuming this is my last node. Okay, this is my last node. So I must have the access to this node, because if I directly delete it, then my tail pointer would not be able to point to this node, right? And I do not have any pointer to reach over here. It's not a doubly linked list. If I simply change, if I tell you that you have a pointer in both directions, then you can simply use the tail, the tail pointer which is over here, right? Use the tail pointer. You can draw it a little big. Okay. So this is one node and it's pointing to the last node. This is the ending node, and my tail pointer is pointing over here. Fine. Now you see, I don't have any link in the opposite direction. I cannot go from this tail node to this node, right? I do not have something like this. So that's why I must, in order to delete this node, I must also ensure that this tail value is moved to this node, right? Because otherwise my tail thing would be lost. I have to point my tail, over here. But that I cannot do because tail is on this node and there is no way to go the opposite direction. So that's why I have to actually use the head pointer and traverse the whole linked list to reach this node from start. Tail is useless in this case because it's not a doubly linked list which has a direction in the opposite as well. So I would come from head, traversing all the way till this node, and then I would do the deletion. Right? How I would do the deletion? Simple, just simply let's say PTR is the pointer which I use to reach this particular node. Then what I would do is simply do PTR dot. I would at first do tail equal to PTR dot next. That also suffices. And PTR dot next equal to none. I would. Right? PTR arrow next equal to none, and tail equal to PTR. That's it. Okay. So, but in order to do that, at first I must have a while loop, while PTR arrow next, right? PTR's next, right? The next value until and unless actually PTR dot next is. Until this, you simply iterate through the loop. Just, I mean, I'm not doing anything. After you come out of the loop, then you just simply iterate this. Okay. So since this while loop would go for starting to end, assuming that PTR was initialized equal to head. Right? So that's it, it's done. It would take order n time.
Hello, sir.
Yeah.
Sir, I have a doubt in this one. Suppose we have a list, right? And we want to make it a linked list. Suppose, can you write it down?
What I did not get. I have a list.
I have a list, suppose 2, 5, 9, 11 or anything.
2, 5,
5,
9,
3,
3,
9,
okay.
11.
Okay.
So it is also a linked list because we can make it as a linked list.
Okay, so okay, you say what you want to say.
Because linked list is a abstract thing, na? So any
Linked
list can
list
be
is an abstract thing. See, the idea is if you write, so when I am saying linked list, I am saying array, I am saying list. All this in terms of coding is represented using the programming language. Now, if you are only saying using Python, and if I write something like x equal to this 2, 5, 3, 9, 11, this is never a linked list. Okay, this is not a linked list.
So how can we write a linked list?
Yeah, so linked list we have done, right? In the lectures, you have to create two separate classes. The first class would be the node. The first class would be the linked list. It would represent the head pointer. So it could be just a class, and that would be, let's say, linked list. Okay, I'm just defining in pseudocode. So let's say this is the linked list class which has a head pointer, and in this case it's a tail pointer as well, and the next pointer. Next would be as a part of the node. And then again you would have another class which is node, right? And inside the node class you would have parameters like the value, right? Data, whatever the data is, this value, and then you would have the next pointer
And
in order to, and the previous. In case of double linked list, you can do the previous. In case of single linked list, previous is not. And then you have the insert method and the constructor inside it, and then you initialize the value, all those things. So basically, the head pointer would be passed in the insert method of this node, and you can operate along. I mean, that's the whole linked list concept which has been discussed in the lecture.
Yes.
So yeah, so if you want to say how the implementation of this list, Python list, how is the implementation of Python list? It's not a linked list, it's not even a direct array. It's an intermediary between both of them. So we have also discussed that in the lecture. Also, it's there. So it states the. So see, what it happens is when you write 2, right? What would happen in a normal array is, if you just define it, right? Assume this is a normal array. Then exactly at the first position 2 would be stored, then 5 would be stored likewise. But when in a list, in a Python list, you are writing 2, 5, 3, 9, 11. Now assume that this is a Python list. In that case, it is stored internally as something different. It is stored as, let's say, 0x f1, 0x a whatever. I'm just writing it arbitrarily, a6. What does this mean? These are actually addresses where the particular value is present. Okay. Now these addresses are obviously discontinuous. You see that ff1, I mean, okay, doesn't matter. So these addresses are discontinuous. It's not consecutive. In array 2, 5, 3, 9, all of them are consecutive. So if I assume that 2 is located at 1004, then 5 would be located at 1, assuming depending upon the size. So assuming that 2 is integer, which is let's say 4 bytes in size. So it would be 1004, then 1008, right? 4, 5, 6, 7, then 8 is 5, and then 1012 accordingly. So basically, this is contiguous in memory in the situation when this is an array. But if it is a Python list, then it's stored like this: 0x of, let's say in that case, if I take simple numbers, 0x, okay, not 0x. Let's take simple numbers like this. Let's say 2000 for the first element address. For 2 it is 2000. For 5 it is 3000 or 3000. For 3 it is, let's say, 2004. It's totally random, right? Now this memory dot 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 whatever elements are there, this is stored in the form of an array list. Internal implementation of list is, it is implemented in the form of an array of discontinuous memory location. So it is, that's why I said it's both an array and a linked list, because in a list, in an array you have contiguous memory, right? Here it is not there. Here it's not contiguous. 2000, 3000, 3004 are not contiguous, right? But this collection of address itself is an array. So if I write x of 0, that essentially means the address 0x2000. Okay, x of 0, x of 1. Fine. Now when you write x of 0, it goes to the first address, it sees it's 2000, then it would go to the memory's 2000 address and fetch the value 2. 2 is there, huh? Fetch the value 2. So it is discontinuous, unlike array. And again, it is implemented in the form of an array of addresses. Only thing is, these addresses are discontinuous. Now, discontinuous address means linked list. And but this address itself is in the form of an array. That's why it is also an array. And that's why you can actually do indexing. That is the answer why you can do indexing on list, Python list. Fine. So that's the structure of Python list. But generally speaking, classically speaking, arrays are contiguous memory locations. Linked lists are it's discontinuous, connected using pointers. Pointers is in this case the next variables. Fine. Yeah, you want to say anything?
No, sir. Actually, I understand. Actually, I am confusing with this one. So how linked list is stored the next value and the previous one. Suppose I'll give you an example 2, 5, 3, 9, 11. So if we count this 3, take this 3. So the next node with 3 is 9, and the previous one is linked with 5.
I mean,
So,
if you simply write this statement, it's not a linked list. In order to create this 2, 5, 3, 9, 11 in the form of a linked list, you have to create this class
the
node
class.
and class linked list. Then you have to call the insert function. In the insert function, in place of data, you would write equal to 2. Then in the next call of insert function, you would write in place of data equal to 5. Right? In place of data, you put this 2, 5, 3, 9, 11, whatever. And whenever you are calling the insert function, you also have to take care of the next, previous, all these pointers. So that's the whole linked list insertion deletion.
So every time we have to make the linked list, so we make that class nodes and all.
Correct,
right?
correct.
Okay.
You make one node and put the value, and then properly place the node in the pre-existing linked list. Okay. So yeah, it's better if you go through the lecture, it would be clear. All these things are discussed.
I watched, but actually I didn't understand. That's fine.
Okay, so I think then live session.
Yes, now it is clear. Yes.
I mean, you can also go to the particular week's live session and check the linked list for.
Okay.
That would be much clear. Now, see.
Sir, I have one question. Sir, if you have tail, then why you have to traverse the whole?
How will you come to here? No? See,
sir, tail, I already have tail. I have 2 pointers, head and tail.
But okay, so let me, you just tell me what you have to do when you are deleting the last element. What are the statement that you would write? Just tell me that.
So
When you are deleting the last element, got it, na?
Yeah.
So if you are at the last element, right? So that's what I was saying. This is the node and this is the last node. This is the last node. Tail is over here. Correct?
Yes, sir.
In order to delete it, what you have to do? You have to actually
know.
Yes, this pointer you have to eliminate.
I have to point a last tail to that point. That
correct. You have to put over here none.
Yeah.
You have to delete this pointer which is linking the last node, because you want to delete the last node. You have to delete this pointer, this bridge which is connecting the last node, and in place of that bridge you have to write none.
Yeah.
So that means you need to access for this element. Sorry, this node, but your tail is over here and there is no pointer in the other direction. Right? There is no pointer like this. So I cannot do anything using the tail. I have to travel from the first.
Sir, if the pointer is there, then the order is
Just
order to
order one. It would be
order
order
one.
one.
Yeah. Okay.
Let me
thank
just change this question and ask you that what would happen to the answer if this is a doubly linked list?
1, order 1.
All which option would be correct then?
I think it's a D option or C option. Something is there.
Yeah,
B
now say.
option.
Option B.
B is.
Everything would be order one.
Thank you.
Sir, I have sir, whenever we make a linked list, so does whenever we make pointer, doesn't that pointer actually occupy some space?
Correct.
Because sir, of course, if a data will occupy a space in the memory, but will pointer take a some space?
Yeah. Pointer would take the same space as your. Okay. How should I explain? So I mean, so the address, right? Every computer. So see, first of all, whatever computer has, it can only access the RAM. It cannot access the hard disk. But obviously, you use the hard disk, right? So how it accesses the hard disk? There is a separate concept on that, and that is addressed in the operating systems concept. But okay, let's assume that the processor can directly access only the memory which is there in the RAM. It does not identify the hard disk. Processor even does not know that there is a existence of some hardware which we call the hard disk. It does not know about the existence of hard disk. It only knows about the existence of a primary memory or the RAM. Now, as you said, that pointer, whether it takes some memory or not. Pointer would take obviously a memory, and pointer is what? It is pointing to an address, correct? Which is this address? I told you processor can only identify the RAM. That means any address the processor can identify, it must be a RAM, and the address bits, the number of address bits in any address of the computer would be equal to the number of bits required to represent the RAM, right? Or let me state it in another way, the number of bits in any address of a computer would be equal to the number of bits of the address register, or let's say we don't want to go into those. Let's say, I mean, there is a limitation on the number of address bits that you can take, and that is actually equal to the size of the RAM. Fine. And someone is on unmuted. Can you yeah. So basically, therefore, any pointer, since it is storing an address, it would occupy the same space as the number of bits that is required to identify any address. So if you are working on a 32-bit system, so your pointer would take a space of 32 bits. If you are working on a 64-bit system, your pointer would take a space of 64 bits. Okay. So in CT, was this address L value, R value? What is L value? What is R value of a variable? Are these things addressed, or did you all hear about all these things? So you all have obviously learned about variables. Now, what is L value of a variable and what is R value of a variable? Can someone acknowledge whether you have heard or not heard, whether it has been taught or not?
No, sir.
No, sir.
Okay, fine. So I mean, we have discussed it in the previous time in DBMS. Okay, so let me finish this, and I would reply on discourse about it. Okay, regarding the size of the pointer, not directly related with algorithms, but since this question came up, I would discuss on the discourse. I would add a post. Fine.
And just to add to this question, sir, I mean, can it be the same question be asked in the situation when there is no tail, either doubly or singly linked list?
When there is no tail, acha.
Tail.
So when there is no tail, you cannot even go to the last node, right? It doesn't matter whether it is double or single. You have to travel from the first one.
Mm-hmm.
So anyways, your insertion at the start takes order 1. Your insertion at the end takes order n. In doubly linked list, where tail is not there. Your deletion from the start takes order 1. Your deletion at the end again takes order n, because yeah, even though it is doubly, you have to travel from start to the end. I mean, penultimate, not the end, just before the end.
Okay, so I mean, if tail is not there, then also this question can be framed similarly, but the answer
Yeah,
will
yeah.
be framed accordingly.
Yeah, yeah.
Okay, thank you.
By the way, so this is now, see, this class node is there. We have a node and the linked list is, assume we have a class linked list which head refers to the first node of the linked list. We discussed exactly that thing, right? You have a class linked list which has head and tail, and then you have class node which would have data, next, and previous. So here is the class node. Here it's a singly linked list. So previous is not there, next is there, the data is there, which is represented as the variable value, and we have a class linked list, and that has the head node, head pointer. That's it. And we are assuming that this is the class node represents nodes of the head pointer, because we would call the node functions using the object and pass the linked list over there. Anyway, so that's not something that is asked over here. What is asked is, you have this function, right, reverse, and this reverse function is reversing a linked list. Now, what I'm doing is, the reverse function, to go to the question just a bit above, see over here, this method reverse should reverse the linked list when invoked, like reverse L dot head none. Right? So in place of current, I am passing initially L dot head. L is the linked list object, right? And previous I am passing none. Fine. Previous I am passing none, and in place of current I am passing the head of the linked list. Assume there are some nodes already there, and then you are calling this reverse method. Right? And this reverse method should reverse the nodes of the linked list. That is, if the nodes are like this, let's say 2, 4, 9, right? What you have to do is, you have to just, okay, let's draw it over here only. You have to just reverse these edges. This is what you have to do in the reverse function. So what should be in place of the block 1? Right? This kind of question, someone was asking about the programming questions, whether it would come or not. This kind of snippet kind of questions might come. Okay, so how do we solve it? So you just have to think about it. I mean, I'm just going into the explanation directly. Just carefully think about it. Some observations we would make at first. So first of all, we see that there is no loop in the code. Right? There is no loop in the code. We know that if we are traveling through a linked list, it must have a loop, but it's not there. What you see over here is a recursive call. Right? Fine. That's our first observation. That's it. I mean, there is no loop. Now let's proceed further. What we see in the other parts of the code, we see that if current.next is none, current.next is none. Correct? What is the, in the first iteration, when we just called the reverse function in the first time, what was passed to CURR? The current, I mean the cur variable, what was passed? L dot head. That is the head pointer of the linked list. Here I am checking in the very next statement whether the head pointer, I mean the current.next is none or not. That is the just the node after the head node, in this case in the first iteration, whether that is empty or not, whether it exists or not. Right? Now see, the thing is, if I'm checking current.next is none, that means this is a check for end of the linked list, right? That's what we do when we want to check the end of the list. End of the linked list. But here we do not have any loop, but still we are trying to check the end of the linked list. That means this block of code must have some lines of code, right, which would actually increment the head to proceed, not head, the cur, the CURR, the current pointer, to proceed through the linked list. No loop is there. So only way I can do the proceeding or traversing through the linked list is using the next pointer. Correct. So what I would do is I need a next pointer to travel through the next node. So my one line of statement would obviously be, and since you see here I'm passing temp to the next invocation of reverse in place of the cur variable. Temp is not here in place. I mean, I cannot say temp in the part in the code which is given. So I must have a variable temp, and I'm passing it in place of current. That means this means I'm traversing, right? If there is no loop, I must have recursion to traverse to the list. And I'm passing temp in place of current. That means that is the next node. So temp is the next node, the next current node, right? The next node. In the next invocation, that would become the current node, right? So that essentially means in this block of code, I must have the statement saying this line of code, that you do the current arrow next, that is the next is placed in temp, and then you simply pass the temp to current, right? And simply what would happen for previous, if that is the situation for next, right? In previous, we would just simply do the separate thing. Just the other thing, that current dot next, not dot, current arrow next is equal to the previous that has been set. Now, what do, if you did not get it, let us again discuss it. So what does happen? What is happening over here?
Can you do with that example? It will be more easy.
Sure.
Thanks.
So let's take this code. Assume this code is there, and now let's apply it on this info. This was my initial list. Okay. So
Can we add one more element so that it will be easy?
fine. Okay, done. Okay. So my head pointer was over there. Let me remove the color. At first, my head pointer was over there. Okay. And I passed that head pointer in place of the first iteration of current, right? I mean, first iteration of reverse in the current variable. So my current is also over here. Done. Then what I'm doing, current dot next is none or not, this line. Current dot next is none or not. Okay. I see that, it's not none. Current dot next is equal to 4. And not 4, sorry, I mean this node, right? Current dot next is this node. So it's not equal to none. So what would happen? I would go to this part of the code block. Acha, can someone just tell, do you see my cursor now, wherever it is?
Yes, sir.
Yes, sir.
Now can you see the cursor?
No, sir.
No.
No, sir. No.
No problem. Fine. Okay, so my current is over here in the first node, right? And I have just checked this condition, if current dot next is none or not. It is not none, it is equal to the fourth node. So what would happen? I would come to the out of the if statement, which is the block 1 over here, and I have given that temp equal to current arrow next is the first code in the block, the first line of code in block 1. So what would happen when this is happening? My temp would be one variable, and I'm putting currents next. Current next is what? This node. This is current. Yeah. So current next is this node. Correct. So I am putting. It's not 4. It is the node code. I mean the node which is having the data field equal to 4. So it is equal to the node actually. So current arrow next is this fourth node, and that's where I'm putting temp. So temp is over here. Okay, current is still in its position. After that, in the second statement over here, I am changing current. I must move current now, right? Because current should be the previous node, right? So why I am saying this is, see, here I have one previous variable. So in the next iteration of reverse, so I'm calling here the next iteration of reverse, right? In the next iteration of reverse, if temp is the next node, what is temp? Which is current dot next. So that means if in the next iteration, the next node of current is the current node, try to get this. In my iteration, whatever is the value of current, in the next iteration, the next node would be current, right? So in the next iteration, what would be previous? In the present iteration, whatever is my current, that would be previous for my next iteration. Okay, so that's what I'm doing over here. So before passing the previous, I'm just setting the previous to be equal to current dot next equal to previous, because I'm passing this current now. So what would happen? Let me just go through again. What I mean is temp is settled over here. After that, I'm doing current arrow next equal to previous. Okay, current is over here in the first iteration. Current dot next is what? Current dot next is this field, this arrow. Right? Now I'm setting that to be previous. What was the value of previous in the first iteration? It is none.
None, yes.
Right? So what would happen? This link would go away. And here I have set it to be none. Right? Fine. And then what I'm doing is I'm passing this to the reverse. I'm calling this reverse method again. Fine. I'm calling this reverse method here, and I'm passing temp, which is my current, which is over here. And current is now equal to what? I have said current arrow next is previous. That I have done. Correct? So that I have said to be this thing, none value. Now I have gone to 4. Okay. And what would be the value of previous? Now I have passed current, right? So where should my pointer previous be? Previous is over here.
2, right?
Correct. So previous is over here. So in the next iteration, in the second iteration, what would happen? Current dot next is none. So where is current? Current is over here on. Sorry, where is current? Current is over here because this is my next current. Temp is the next current, right? So my current has moved because this is the second iteration. What I am passing into current? I am passing temp. What was temp? Current arrow next. So that's why temp is over here, and accordingly my current is also over here. Current and temp are same. And what is previous? Previous is in this case 2. Now I check it's null. No, it's not null. Again the same step. Again I go to block 1 and I do current arrow next equal to temp. Right? Current arrow next means what? Temp would move from here to.
So how is the current not next pointing to 2 when previous was none?
What is this? You have this temp now. You are passing the temp to current. In place of current.
Yeah, that's fine.
Then
the second one here it is current dot next is equal to previous. So previous was none, but where is the value of previous changing to 2?
Here we are passing CURR to previous. Correct. We are passing CURR to previous. Current was initially over there.
Okay. Yeah. Okay.
Okay. Fine. So here is my temp at 9. Current is still at 4. Current is still at 4. I have not changed anything for current. So what is happening? Current arrow next is equal to previous, the second statement. I have only done the first statement where I moved the temp. So I have moved the temp over there from 4. Now the second statement I would execute, which is current arrow next equal to previous. Now you say me what is the previous? Previous is this node, right? Over here.
4.
Correct. So, and what was current? Current is 4 over here. Current is 4. Okay. So now I would set current dot next, current arrow next equal to previous. That is done. Fine. So current arrow next is previous done. So what is next? What is this thing? Current arrow next means which one? It means this particular pointer. Current arrow next means. Now in place of current arrow next, what I am doing is I am putting previous. Previous is 2, isn't it? So if in place of this pointer I am putting 2, what does it mean? It essentially means you are doing this. Or if I draw it properly, simply that's what you are doing. Got it? Current is this one, correct? Current arrow next means the next field, the next node. So in current arrow next, I am putting previous. What is previous? Previous is 2. Right? So that's it. You just reverse the first pair of nodes. Now in the next call, so now I would again go to the, so my block of code is finished, and now I would go to the next call of reverse. Right? And what would be passed inside temp? Again, current arrow.
Sir, after this call, the 4 and 2 become will swap.
No. We are not swapping. We are just simply changing the pointer, right?
Because now the temp is pointing the 9, and the previous is pointing 2. Right?
No. There is no previous field. What I'm saying is, if you go to the node, and let's check the structure of the node. There is only next. Fine. There is no previous. So if you think that here it was some value, right? But here it is actually none. That's what it means. That we have set it like this, and then I have this value which was next over here.
After the first call, the previous become 2, right?
Correct. And that's what I'm doing. In the 4, I'm pointing it to 2. Okay. So initially it was, 2 was from here to 4. This was like this, but we deleted that and set it to be none. And then in the second call, I am setting the next of this field, which was like this, to 9. I'm deleting this, not deleting, I'm modifying it to point it to the second node. So these are just pointers. We are not swapping value. We are just making the pointers point to different memory locations, which are the nodes, different nodes. Okay. So you simply move this pointer, current arrow next equal to previous you are doing, previous was 2. So you simply move this pointer to previous. Don't think that there are 2 pointers like this and here we have 4. So it is moving that way, it is moving that way. No. There is only one field in the node. It's just a matter of representation. There is only one next field, and that next field is actually this pointer. Okay, this is not a doubly linked list. Okay, so like this you do. Now again, current is over here, and in the next reverse call, what would happen? Temp would be passed to current. So what is temp now? This is the 9, right? And I have done temp equal to current dot next. Yeah, so this is 9. And sorry, I think that iteration was done, right? Yeah, that iteration was done. So I would next go for the third iteration for 12. Temp would be passed to 12. Just like the same thing, it would be just repeated now. And current would be the next value. Previous would be the next value, which is 4. Sorry, I have not done this iteration. This is previous. This is temp. I have not yet done the previous iteration. Yeah. Okay. And then again you simply repeat those steps, and obviously now current is equal to temp because you have passed this temp in place of current, right? So current is moved from 4 to 9. Again same steps. It's not none. It's obviously not none. This would be executed. Then current arrow next is put in temp. So temp is moved from here to Sorry, just a second. Okay. Temp is no. Give me a minute, there is some system issue. Can you all see my screen?
Yes,
Yes, sir.
Yes, sir.
Showing not responding.
So,
Now it is
can,
fine.
excuse me, sir.
Uh-huh.
So can we say that like with each iteration, what we do is we are basically carrying the same node twice, while one such passing of the node is so that we can basically shift it to the next one, and the other variable is just used as the pointer so that we reverse the
We have
next
the
one.
record. We have the record of the previous one. That's it. Yeah, we are doing that, right? Simply we are making the temp equal to next, passing the temp into current node. So basically we are essentially, you can simply write current equal to current dot next, right? When you normally write a traversal function.
Yeah.
So that's what is simply done here, just in the form of recursion. When I'm passing temp into current, if you just merge these two things together, what you are getting? You are getting current equal to current dot next. Right. So this is temp is passed in current now. So what is temp? This is current. What is this statement? Current equal to current arrow next. You are simply traversing that, and when you are in the next node, you need to have the record of the previous one, right? Because you deleted this connection, I have deleted and made it point the other way. So if I've deleted this, I must have a record of the previous node. Otherwise, I would not be able to change this pointer. Just like I deleted this one and pointed it in this direction, I cannot do the change over here if I do not have the address of it. So I would simply make this pointer also point like this.
So instead of this, if it were like an iteration, like we would have the same variable previous from the original call, like after current dot next, and that would equal to current, and then we will like iterate it.
Yeah. Do that. Fine. So okay. So I have discussed this. It's not something very theoretically understand. I mean, very difficult. You just have to observe the iteration and it works. Okay. So by the way, the option and one was the answer. So this one. So hashing, what you do is simply you have these keys, right? All that is asked is if the keys are coming in this order, right? In the proper order, then in which of the options I would get the same hash key, which is given over here. Right. That's the question. So let's say if I have 11, right? Where would 11 be placed? Forget about this part. I am drawing it on the left hand side over here. Just concentrate over here. This part you would see.
What is the hash function?
Hash function is mod 5. Hash function is key mod 5. Okay. So I have 11. Okay. So I would be placing 11 over here. Then I have 23. I would be placing 23 over here. I have 35. Then I would be placing 35 over here. 20. Mod 5 is again 0. So here 20 should have come. But 20 cannot come because 35 is also there. Now it is using linear probing. If you check the question statement, it is said that it would use linear probing. linear probing, we would travel one by one to which of the next available space we find. So we go to here, my computer is hanging, just a second. Yeah, so we come over here.
Next available space it will find linearly.
Correct. Next available space. So it finds over here 20 is, no, it cannot place because 11 is there. Here I have got an empty field, so I put 20 over here. And so that is sorted. After that 14 is obviously mod 5 put 4. So this is the sequence that I would get if this is the order in which the values come. And I would see that, let's delete all that. And I see that obviously it matches with the given hash table, 35, 11, 20, 23, 40. Fine. So now let's do it for the second sequence. So first one is a proper sequence, and that's why it's one of the correct answer. Next one is 14, 35. So put 14 over here, 35 over here, 23 over here, 11 over here, 20 over here. Sorry. Yeah, 20 it would come to at first. Similarly, it would come to 0, but 35 is also there, 11 is also there, so 20 is placed in the first available. So again, I get the same order, and that's why these two are correct sequences. Now let's check for the third one. So 23, place 23 over here, mod 5 is 3. 35 mod 5 is 0, so 35 is placed over here. 14 mod 5 is 4, 14 over here. 20 mod 5 is 0, so over here 20 would come at first, but it would see 35 is also there. So the next available space it would be placed. So 20 is placed over here, but you see that this is a mismatch. We have 11 on the right hand side, the given hash table. And if we insert the element in this order, if we insert the element in this order, then that means this is the list that we are getting, 35, 20, and then 11. Now 11 would again should have been placed over here, but since 20 is coming first, 11 would be placed at the next available space. 11 is placed over here. Fine. So the third option is not correct. It's not one of the answer in which we get this aspect. Okay. Accordingly, if you check 23, 20, so what would be the sequence? 23. Now see, 20 comes earlier over here. 20 mod 5 is 0. I put 20 over here. Now you see this 20 and this 35 is not matching. Right? So this is also a wrong sequence. So A and B are the correct answers, which are the probable hash orders in which the table would look like the one given in the question. Any doubt on this? Pretty simple things, but if you know the hashing concept, it should be clear. No doubts, fine. Consider the following statement. The back button of a web browser internally uses a queue to browse back through the history. Okay, so which one is the correct statement? Someone wants to say which option is correct?
2 is correct.
2 and 3.
So statement 2 and 3 are correct?
Yeah.
So
Yes,
about,
yes.
So that means option B is correct, right?
No, C. C is the answer. 1 is
Only
false.
2 is correct.
So only which one? Which option is correct?
2 and 3 is correct. Only 1 is false. So it is C.
No, only third statement is correct.
Only one
Which one
is
is
false.
that?
2 and
See,
This
only
browser
the
uses that.
only statement 1 is false, and 2 and 3 are correct statements. So if you see, the last element to be inserted into a queue will always be the last element to be taken out of the queue. That's correct, right? If you use it first in, first out. The other way to say it is last in, last out. So whichever came in first would be taken out at the last, right? Sorry, whichever came in at first would be taken out at first, because it came at first and it stayed and then it would go out, right? So FIFO order. So last element, whichever you inserted, will always be the last element to be taken out, because at first the first element would go out, then the second element, then the third element, and at the end the last element which is inserted, that won't go out. So third option is correct. Third statement is correct. Back button of a browser. So what happens in a browser? If let's say you are on Google, and let's say you are on your mail, and then you go to the IITM portal. Okay, if you press back button, you go to the again the mail, right? You don't go back to Google. You started your journey with Google, you went to the mail, and then you went to the portal. If you press back from the portal, you would go to the mail. No, you will not go to the initial starting state of Google. Correct. So what is happening over here? Whichever is the last value that has been inserted in the, not inserted, whichever is the last value which you visited, last website which you visited, if you press back, you would go to that website, right? So what is this?
Stack.
The last in, first out, which is stack. So whichever came in last is going to be taken out first. So the website that you visited last, once you press the back button, you go to that website first, and then accordingly you would go to the, you go through the chain of website visits. At the end, you would pop the first home page with which you started your surfing. So that is basically a stack. So option 2 and 3 are correct option. Option 1 is wrong. It's not a queue. So this question is based.
Sorry to interrupt, sir. I think this is the last statement of yours. So what is the correct answer for that?
Correct as only one statement is false. 2 and 3 are correct.
Okay, got it. Yeah.
If the last element is the one to be taken out first in a queue, then the first one should be true, right? Because
no. In a queue, last element. So what is happening? So tell me this thing. So if this is a queue, let's say this is a queue, and from this end I would insert. Okay, and
yes,
from this end I would take out or remove. Fine. Now when I would insert, let's say I insert 10, 20, 30, 40 like that. So I inserted 10. So what would be the state of the queue? 10 would be over here. After that, I again inserted 20, right? So what would happen? Once I insert 20, 10 would come here, 20. And then I inserted 30. So 10 would come here, 20, 30. Likewise, at some point, I would have the value in the order 10, 20, 30, 40, let's say up to 50. So my insertion is complete. So if I say which was the first element which was inserted, what is the answer?
10.
Correct. First element which was inserted. Now I do the removal. I start the removal. And I do the removal from this end, right? So the first element which I would remove is 10 because it's nearer to the remove end. So what is the first element to be removed? Which is removed.
The first one which was inserted.
Correct. So what is what? First in, that is only first out. 10 is the first in, 10 is the first in. And if I say that which was the last element to be inserted, 50. Accordingly, after 10 is removed, 20 is removed, 30 is removed, 40 is removed, then 50 would be removed. So last in, last out. FIFO is same as fine. Last in, last out. In case of browser, when you press the back button, What is the last in? Last in is just the website which you visited just earlier, right? Just before coming to the current page, whichever is the website you visited just before that, that is your, I mean, the last out value. But is it your last in? No, right? Because you have the last in is the first value which has been coming. So it should be the last in, first out. Whatever is your whichever your element you are just extracting, right? First out. That should be the last inserted value in case of browser. So your last web page should be the first value to be taken.
Sir, got it.
So that is LiPo, and that LiPo is used in scan. Fine. So this question is basically it's asking you that if we perform a binary search on a linked list, and here linked list means a proper linked list. It's not an array. It's not a Python list. It's a proper linked list which you have created, and on that you apply binary search. Then what would be the time complexity of that binary search?
C.
Option C, yeah.
Of n.
Order of n, correct. Why it is order of n? Because if this is my linked list and it is sorted and everything, right? Let's say 1, 2, 3. Fine. But the problem is in list or array, whenever we implemented binary search, it actually should be array ideally. Whenever you implement binary search, the facility that we took is start plus mid by 2. Sorry, start plus end by 2, right? Or accordingly, start end minus start by 2 plus start, whatever. Basically, we were dividing into 2 to get the mid value. Now, whatever we were doing is ARR of mid. We were writing this statement, right? ARR of mid. So we can directly do indexing. So what is this? This is indexing. So simply by dividing a number by a constant factor of 2, whatever index we are getting, we can put that index inside the array and access the array element. So this is called indexing or direct addressing. But can you do that in a linked list? You cannot do that, right? So you have your head pointer over here, and let's say
I have to traverse through the list.
Correct. So you cannot write something like head plus tail by 2. Okay, these are pointers. It would be nothing. What you have to do is you have to traverse this list like this, like this, like this, and come in the middle. And come over here, which is the middle. Let's say I'm considering so these two are both middle elements. I'm considering 4 as the middle one. So I have to traverse this long. I have to traverse like this in order to come to the middle. Fine. And then again apply my binary search whether my p is greater than 4 or less than 4. If it is less than 4, then I would then again do search over here. That is, I would come to the middle by traversing like this and then apply. So basically I have to traverse. I cannot just write L plus R by 2 or whatever and I would get the index. Right? And since we have to traverse like this, in worst case it can be actually order of n by 2 because I am traveling to the middle, and which is essentially order of n. Okay. So it doesn't matter whether you apply binary search on a linked list, which is not contiguous, unless and until. Who is the superhero over here? The superhero over here is indexing. Only because you could do direct indexing, and this mathematical simple sum would give you the index value mid, right? And you can put that answer into the array and use it, which we call indexing. This was the feature which created the binary search time to be longer. But in a linked list, you cannot do the head pointer plus tail pointer by 2. It would not happen, right? So that's the problem. So you have to traverse to the middle, and traversing to the middle takes order n by 2 time, which is essentially your order n time. Now there is a theoretical question, and directly stating BFS systematically computes reachability in graph. Correct? You check for you apply BFS and check whether all the vertices are reachable or not. Complexity of BFS is order of n square. Yeah, because when you apply BFS using an adjacency matrix, what you do is basically you travel through all the possible the neighbors of particular vertex, right? So can someone tell me when would be the worst case happening? This order of n square, assuming that you are using a matrix.
C point is correct because we cannot use BFS for cycles. Only DFS can be used for cycles.
Both BFS and DFS can be used for cycle, right?
Yeah,
Yeah.
Yeah.
You can apply any one of them. Okay, so what I'm asking is, I would come to the third point and all those things later. Let's go one by one. So BFS systematically computes reachability. That is okay. Anyone has doubt in that?
Yes.
That is
No,
fine, right? Okay. So second question is, my question is, forget about the correctness of the statement. Complexity of BFS is order of n square, right? So can you tell me a situation when it is order of n square, or is it always order of n square? I mean, using adjacency matrix. Assuming you are using adjacency matrix, will it be always order of n square, even if you use adjacency matrix?
Yes, because you
Sir.
need to find this thing, right? The neighbor in each of the cell of the
Correct.
in each row you have to check throughout the
For
function.
each column, we have to check for a particular node. So for like there is a node or
We have to traverse all the column.
one,
for each
then
one. Yeah.
we have to traverse all
Yeah,
the
exactly.
column to find
Correct.
its neighbors. So it's
Correct.
always n square.
Exactly. So many, I mean, this question has been asked in some place, I don't remember. So some students said that if you are using an adjacency matrix, then also the worst case would only happen when it is a, okay, let me just ask the other way. This answer is correct. Adjacency matrix, if you use, BFS would always take order n squared time, because you have to check the columns and then again check, I mean, you have to check all the neighbors, and therefore you are checking for each row all the columns. So that is n squared. But let me just ask this: when you are using an adjacency list, right? Not a matrix. If you are using an adjacency list, where you only have the edges and the nodes which are connected to a particular node, only those edges you have. In that scenario, I have the complexity as order of n plus n, assuming m is vertex, m is edges, and n is vertex. Can it go to order n square, or will it always be order n plus n?
Neighbors of the list is have one vertex have neighbors of all the lists, then it will be order of n square.
One vertex, sorry, I could not get.
One vertex have that can reach from every vertex.
Or you can
Only
say
one?
every vertex is connected to all other vertices.
Exactly.
Yeah.
Exactly.
Yeah.
So this is m plus n, right? Edges plus vertices. Now it is already n is there. So only way to make it as order of n square is if I can do something with m, right? Because it is n. N can never become n square. I have to do something with n, which is the number of edges, right? And that means basically I need to make as m as n square, some function of n square. I have to make m some function of n square. Then only my complexity would go to order n square. That would happen in a complete graph, as you said, that when every vertex can be reached from every other vertex.
Every other vertex. Yeah.
What would be the number of edges in that case? What would be the exact value of n? Not only n square.
Yeah, m is equal to n.
Minus 1, right?
No.
Edges are always n minus 1.
n minus 1.
No. This is not in BFS tree. This is in the
M,
graph.
m is equal to n.
No. In the graph, what I am saying is, when you are getting this case, order of n square, you said correctly that every vertex must be reachable from all other vertex. What is the meaning of reachable? That means every vertex has edges
Yeah, so you
from
have
all other vertex. Na?
N plus 1 by
n
2.
into
N into n minus 1.
n into n. Yeah, exactly. N into n minus 1. So for each node, you will have n minus 1
m into
edges. N into n minus
n into
n minus 1.
That's it.
N minus 1
Yeah,
by 2.
the total number of edges.
No, we'll be doubly counting it. That's why
N
divided by
minus 1 by
2.
2.
N into n, is it the answer? N into n minus 1. That's what I want to ask. Or there is something else?
So we'll be counting 2 times in this. That's why we divide.
Connected or non-connected will
By 2. It's undirected.
I think by 2. N into n minus 1 by 2.
Correct. See, very simple thing. What I am doing, how you are getting this thing? You can interpret in many ways, but the very simple interpretation is, since you all have learned combinatorics, the simple interpretation is M is edges, right? What is an edge? Edge is connection of two vertices. So you have n vertices, right? So how many edges are possible? If a particular edge is connecting two vertices and you have total n vertices, so how many total possible edges can be there in choose two? That is, you have n vertices. Among those two vertices, among those n vertices, you are picking arbitrarily two vertices, right? So how many such possible pairs of vertices can you pick from the n vertices? That is essentially your number of edges, right? And n choose is 2 is n into n minus 1 by 2, by the way.
So, but that is only if it is undirected, right?
Which one?
That happens like if the graph is undirected, right? Oh, okay, yeah. I missed that. Sorry.
Fine. Okay. So that's the scenario, and if you simply convert in order of, it would be order n square in minus n by 2, which is basically order of n square. So your order of n plus n, even if you use the adjacency list, but if your adjacency list is of a complete graph or mostly complete graph, then your complexity can go up to order of n square, which is just like using an adjacency matrix. So when you are actually operating on adjacency matrix, which particular data, when you are actually operating on very large graphs with mostly complete, there are many edges, right? Mostly complete graphs. Then which data structure should you use? Which is adjacency list or which is adjacency matrix?
Adjacency list. Yeah.
List.
I said if it is a complete graph.
Complete in the sense like just the one we mentioned right now.
Both of them are same, right? If it's
Yeah.
if it is a complete graph, both of them is giving you order of n squared time. But there is a but in this, and this is not again required with respect to the course. Conceptually speaking, both of them would give you same performance. When you use a complete, when you are working on complete graphs, it is you can use either one of the data structures. But in practice, you should use the adjacency matrix. Why I am saying this is
because it uses array. Because it uses array.
Exactly. Because why? What is the reason? It uses array, but what would happen for that?
Access will be faster.
Exactly. Yeah. Great.
Direct indexing.
Great. So that's the performance point of view. That is not with respect to algorithmic thinking or complexity oriented thinking. That's more towards the system oriented thinking. So when you have to exactly run programs on the system and benchmark them, so you actually have to also think about what is actual running time, execution time. So arrays provide a much better access time because they are contiguously located in memory. Lists may not be adjacently contiguously located, and it is not adjacently located or contiguously located. Right. So that would take the system would take some time. You would see the same result, but system would take some time to access those elements. But array would be just like a direct access. So system can perform better in a adjacency matrix, at least for the access time. But if there are very less edges, then the access time benefit is not giving you any improvement because your number of edges is very less and you have to still your complexity is n square. But adjacency list would give you something around order of n or something like that, right? But if it is a complete graph, it's better to use the adjacency matrix because of the advantage of matrix operations or matrix access, which is an array access essentially. Fine.
One small doubt in Python in this course, are we differentiating between array and list? I couldn't find any difference.
No, we are not differentiating. We are mainly differentiating between linked list and list or array. Linked list is separate, and list and array is separate. So
yeah,
list
and here we never represent array, right? It just normally we're using only list, right? Both are same in Python.
No. Adjacency list is different, right? Adjacency list is just a dictionary. You remember that?
Yeah, I understand. But my question is, here in this course, we are not using anywhere like array list separately, right?
No.
Now you said list is different. Array is easy to accessible compared to list. You said
exactly.
That question I'm asking. Are we
That,
here?
no. That we are not at least addressing in the later parts of the week, but there is one lecture where sir has discussed about the internal implementation of list and arrays. So if you check that in the week 3, it is the end lecture, I think.
Okay, but in this complete course, most of in PDSA we are just
No,
using list,
no.
right?
Correct. We are
Using
not
array.
correct. We are not segregating between them, but if you check the lecture, difference between list and array, this is lecture 3.9. Okay. In that lecture, the implementation point of view is discussed. The thing that I just discussed now, that is discussed for the knowledge, but for the algorithms in the further weeks, we are considering array and list as same.
Okay. But if you want to represent, there is a separate thing, right? Now, whatever we use in this PDSA, we are doing only list on list, right?
Yeah.
Okay, that's my question. Okay, thank you.
So linked list works like an array, right?
No. List is totally different. Okay, maybe you can check the previous part of this today's discussion only I discussed. You can check that. Okay, so DFS. How many possible orders of DFS traversal are there on the box? So you start from node 3. You started at node 3. Simple thing, DFS is just like a blind person. It would travel in all possible direction, and whenever it sees that there is a dead end, it would come back. So you start from 3.
Sir, what is the question?
You have to simply apply DFS starting from node 3. How many possible orders of
Okay.
DFS is there? How many possible orders of DFS? So see, first order that we can see is from 3 would go to. So I hope you understand the DFS, right? That it's just like what you do in DFS. You simply pass the any one of the next neighbor to the stack. I mean to the next call of DFS, right? And then again the next neighbor. Then again the next neighbor, as long as they are not visited. Once you see a visited neighbor and no other neighbor is there for the current node who is not visited, then you come back. You come back to a point where you get again a neighbor who is not visited. And if there is no such neighbor in the whole path, then that means essentially you have completed traversing the graph. So DFS is essentially your, if I have the DFS function, just writing in short. Okay, whatever parameters over here, you are passing the node and all. So what you would essentially do is visited of someone, whatever node you have passed, visited of n not equal to do, then you simply call DFS of n. That's it. I mean, simply this recursive call would happen, and yeah. So when you have,
there are 3 ways.
Yeah. Answer is 3. So DFS, in order to solve the theoretical question, the best way is it's a blind person. It would go till the dead end and then come back. In that manner, how many possible orders are there? So first is, let's say 3, then I go to 5, then I go to 1. I can go right 3, then I go to 1. Sorry, 5. From 5 over here, I can go to 1. From 1, I can go to 2. Right? 2, can I go to some place? I cannot go to any other place because 2 is a dead end, right? 3 I have already started. I can go to 3 from 2, but 3 is the one with which I started, so 3 is visited. Other than 3, is there any other edges from 2? No. So there is no place. So 2 is, I would stop at 2 and I would come back to 1 because there are no possible neighbors for 2. So I would come back to 1 and search for neighbors. Do I have any neighbor at 1 which is not yet visited? I have visited 5, I have visited 2. So no neighbors. So I would again come back at 5. I mean, I would come back at the node from which I traveled to 1. So I come back at 5. Now at 5, do I have any neighbor which has not been visited? Now I see that, okay, I have one neighbor, 4, which has yet not been visited. So that's my first order. What can be my second order? Start from 3. Now I take this one first. So I go to 4 first. Okay, from 4, I can go over here at 2. Then 2, only one place 3 is there, that has already been done. So again, I would come back at 4. right? I come back at 4. From 4 I see, is there any other node available? No, because this is also, this edge is also like this edge is also like this. I cannot do anything, so I again come back to the vertex from which I came to 4, which is 3, right? So now 3, from 3 I can see that this path I can take to 5 and then to 1. So this is my second possible order. Can someone tell me what is the third possible order?
3, 5, 4, 2.
Sir, 5, 4.
Correct. Then 1, right? Only 1 is left. So I would start from 3, I would go to 5 at first, then I would take this path, come to 4, then I would go to 2, and then I would see that there is no other neighbors of 2 to which I can go. So I come back to, from 2 to, I would come back to 4. From 4 again I see that no neighbors, so I would come back to 5, right? And 5 I see there is one neighbor, 1. So you get 3 orders, the answer is 3. Okay, topological ordering. How many possible topological orderings can be are there for this graph? Right? Is it how many? No, sorry, it's not how many. It's which of the following are valid topological order? Okay, so you know that topological ordering, right? If there is a edge from I to j, then my ordering, any topological ordering should be 1, such that I should not have any such pair of vertices where I have an edge from I vertex to j vertex in the graph, and the topological order is placing j first and then I. If this is the topological ordering and if this is the situation in my graph, then this is a wrong topological order. That's the idea. So basically, if there is a edge is getting inserted into a vertex like this, which is say j and this is I, then in the topological order I must come before j. And depending upon that, you can just think of, let's say, A, G, right? So A is there, okay, A has no dependency, so fine. Then G is there, right? Can G be there? Yeah, because G again has no dependency. So G can again be there, so G is fine. Then B is there, B has dependency of only A. So A has already been done, so B is again fine. E is the next number, the next character. What is the dependency on E? Dependency on E is for B. Now B I have already have over here, so E is again fine. F is the next number, the next character. F is over here. F's dependency is G and E. So obviously I have G and E, both of them over here, so it is also okay. And then I have D. D's dependency is G and B. So before D, I have G and B. So that is also done. So D is correct, and C is the last node which is correct. So A is a valid topological order. Okay, likewise, you just have to apply the concept and check. I am not solving for all the options. Okay, if you have any doubt in the topological order, you can ask.
G should be before A, right? Because it has no, dependency.
A also has no dependency.
So, okay.
So the sequences can either start with A or they can either start with G. In fact, let me tell you, G you can place anywhere because G has no dependency. So you can start the sequence with G. You can put G in between any possible sequence. So if I have A, B, D, then suddenly you put G. Oh, sorry, D has dependency on C, right? So you cannot do that. Let's say I have A, B, C, then I can put, let's say, G. Then I have A, then I can put G or B, C. Then let's say I have A, B, then put, because the thing is G has no dependency and A also has no dependency, but I cannot ignore A because I mean, at first, if I put G, then I must place J. Sorry, A, because all other nodes over here except G, they are dependent on it. Okay.
Great. Yeah. Thanks.
This is a nice question. Now things again on
Sir,
DFS.
after G,
Sorry, you are not audible.
after G, there are no other nodes other than A, which for which degree becomes 0.
Sorry, after G, there are no other nodes.
For which degree becomes 0 other than A.
Other than
in
A,
degree.
yeah.
Yes. So that is why after G, A will immediately follow.
Correct. If you just think in terms of the logic, that's the correct thing, that in degree there is no other vertex which has in degree equal to 0 after you remove G. And if you see the just from the diagram, you see that D, E and C, all of them are connected with B, and B is connected with A. So ultimately, A is the root dependency which we must satisfy. But G is independent of A because G has no in degree. So we can put G anywhere in the sequence. But before everything else other than G, I must have A. Okay, so this question is a nice question, and I think you should try to solve it. Please try to solve this question. Similar question was already asked in quiz 1. That's why, we planned it in this fashion, so both of the purposes would be solved.
Yeah, it's like pre and post numbering.
Yeah, it's pre and post numbering. But what is the
So
observation?
push time is pre, pop time is post.
Yeah. So if I draw the graph, it would be something like my push time is 1, right, for A. So A is obviously pushed at first, and I'm now drawing the tree, the DFS tree. So after that, what is push time of what is the
next will come B.
Correct. Then
it will come C.
Okay.
Now it will pop from C. So C will stop at this branch.
Okay.
We will go back to B.
Okay.
Again, we'll from B go back to D. We'll
Go
come back
back.
to
We have not.
D. From B will branch. From B will branch to D.
Correct.
And again come back to B.
Okay.
Then this is over. We will go back to A.
So D's time was.
Sir, we'll go to E, right?
Between C and there is E.
After B.
No, from B.
From C it will go to E.
1, 2, 3, C is 4. Then I will go back to, since after C I am popping, right?
Sorry. From C it will go again to branch to somewhere. It will
No, from B.
We'll go to B and B to E.
Okay.
And then come back and again to B.
Yeah. So it would go to
there
here
3
4,
branches.
5, right? Then what is 6? E is pulled forward.
Again B.
Correct.
It
So
will
I
be
would go
like
back
a crow feet.
Yeah. So I would go back to B then 6, and then I would push 7 is push right. D is. So here is 7.
Yes.
D is popped at 8, I think. Yeah, popped at 8. And then I would come back to what 8 is there now. Then 9 is for pop time of B.
B, yes.
So 9
Then
is
it will go
popped
back
for
to
B.
A.
So what does it tell you? That is, you could travel all the vertices given in the question A, B, C, D, E just by starting from A. That means in the DFS you had edges from A to all other nodes. You had path, not edges. You had path from A to all other nodes, right? What that means is it's a single component, because you have a path from A to all other nodes. That means there is no node left over which is not connected with A by at least one path. So which signifies that it's a single component, and the question is asking you find the number of components. The answer is 1.
So, but option 3, why is it wrong? Because push times C has 3 and also the pop time is 4.
Correct. Then
So why is that not the correct answer?
Which one is correct answer? This is not option. This
The
is
question is different.
Sorry.
yeah. Please, I will explain. I will explain. See. So, what is this push and pop time? When you apply DFS, as we just discussed in the previous question, that you take some node and then you simply call the next neighbor, right? Whichever neighbor is non-visited, you call DFS on that, and then you again call the next neighbor, the neighbor of neighbor, neighbor of neighbor, all the non-visited neighbors you call. When you see that, okay, I have traveled and now I do not have any other neighbor non-visited, I would simply come back to the previous node. That's what we have been doing in the previous question, right?
Yes.
Now let's see what's happened over here. Now I am applying DFS. So there is a graph on 5 vertices, A, B, C, D, E, and I am applying the DFS algorithm on the graph starting from the vertex A. Fine. I'm applying starting from the vertex A. And push time and pop time, these two things are it's just the sequence, you can say the sequence number or the sequence in which the vertices are pushed or popped into the stack, the DFS stack, the recursion stack, right? So if I'm starting the DFS from A, that means the first node which would go inside the recursion stack or DFS stack, that is basically the A. And that's why you see the push for A is 1, because that is the one with which we are starting. So A is pushed first in the stack. Okay. Now push time I'm writing on the left hand side. That's the notation we have been using for push pop time in the lecture as well. So A is the first node. Now say the data is giving you the push time 2 is for B node. That means A is pushed at time 1, right? The next discrete time is 2. So next what I'm doing is I'm pushing B, which is 2. So you follow the next number, which is 2. 1 is done, so next is 2. So 2, what is happening? 2, B is pushed. B is pushed. So what does that mean? The original graph must have an edge from A to B. And that's why DFS pushed B as the first neighbor of A into the stack. Okay. So, so B is the next. So this is the DFS tree that I'm drawing, or the order in which DFS has traversed through the graph. That is the DFS tree. So A to B, B is 2. So second t equal to 0, time equal to 0, time equal to 2, work is done. What is time equal to 3? When time was 3, what operation has been done? So if I see that 3 is the next time instant and C is pushed. So what does this mean? This means in the original graph, you are now at B, right? At 2 times. At 3 times C is pushed. That means there must have been an edge from B to C in the original graph. And that's why C is pushed as the first unvisited neighbor of B node into the stack. So that is done. So 3 is done. What is happening at 4? So let's search for 4 time instant 4, 4, 4. Here I got 4. So I say pop. So C is pop. So when we are popping in DFS, what does that mean? I am coming back to the previous node. Why? Because I do not have any unvisited neighbor of C. I am currently at C. I do not have even a single unvisited neighbor of C. That means the only nodes which might have edges between from C or between C, right? So those two nodes are A and B. Other than A and B, there is no other edge from C node. C is only connected to A and B. Okay. So
yes, sir.
Fine. So
It's same like pre and post ordering.
Sorry?
It's like pre and post ordering.
Exactly. It is pre and post ordering. Push is nothing but pre. This is post. So what is, by the way, let me just ask you this question. Why are we using the term pre and post? Pre means before something, right? Post means after something. So what is that something that we are talking about? And that's why we are calling it pre-order and post-order. What is that something? Can someone tell?
The time, is it? Like
What?
since we started.
Since we started, so if I consider, let's say B's pop time is 9, right? According to the data, yeah, B's pop time is 9. So what does 2,9 tells you?
Sir, it took
Connected
seven units of time to get the rest.
So whether it is, so whether, see, the numbering 29 is contained within the numbering 110. So we are going to be after A, and then from B we are coming back to A.
Yeah, that is fine. That is, I'm asking a more simpler question. I'm asking is, what does 2 and 9 mean? Not comparing 110 or 3, 4, 2, 9. Simply, if I say that 2 is pre and 9 is post, what is that pre? I mean, that's what I said, right? You said prefix, you said postfix. Why? Because pre is the part of the text before the text which we are considering. So pre something or post something means before something you call pre, after something you call post. What is that something? That is what I want to know. Because
it took six. That there were 6 steps in for.
No, not going to 6, 7, 8.
Connected edge and disconnected.
It's simply the answer
Completely
is
explode.
It's
okay.
from
No,
1
it's
to
not.
3. It's originally connected in the graph.
That is again inference. What I'm saying is, see, when I say pre and post, even if I forget about the graph, forget about this thing, this graph, anything, I'm just asking a theoretical question. Forget about this numerical itself. Just tell me pre number, post number. Correct. With respect to a node, what does it mean?
It means there is some operations done before this doing this.
Some operation, can you elaborate? What operation?
It could be anything.
No, it's not anything. Your answer is correct, but there is a specific thing.
It's maybe insertions or deletions.
Insertion into or deletion into?
Insertions into that push time B.
That stack. The stack, that DFS stack. So whenever you are applying DFS, the pre number and post number of a particular node simply means the time between which that particular node was inside the stack. So the notion, the idea of giving this push time and pop time, the word push and pop over here in place of pre and post is just to indicate that idea. Pre and post simply means pre pushing into stack, post means post pushing into out of stack. Oh, sorry, post popping out of stack. So if you have u comma v as the sorry, not u comma v, let's say t1 comma t2 as the pre and post number respectively for a particular node x, that means at t1 time the node x was pushed into the DFS stack, and at t2 time the node x was popped out of the DFS stack. And in between that, whatever neighbor we had for x vertex, x node, their pushing has happened and their popping has happened. And that's why we say, in this case, if you see in this diagram, in this part only, you see that 2 and 9 is there. So 2 is the pushing time of B into the stack, 9 is the popping time of B out of the stack, and C's pushing time is 3 and popping time is 4. That means C is obviously connected to B by an edge. And that's why once we have pushed B into the DFS stack, after that we pushed C. Since we are pushing C after that, that's why its pre number is greater than the pre number of B. It's 3, pre number of B is 2. It's simply the time during which a particular node resides in the stack, that is the pre and post. Pre that time is pre number, post that time is post number. Okay, and that's why we have actually used the more practical term in this question, which is push time and pop time into the stack. Fine. So hope that should be clear.
So component 1 means the whole graph is connected and there is no break in two different.
Yeah, that's what we were doing, right? So I was just discussing. Let's complete that. So
So
I have
if
not-
there would have been say something like F for which push time was say 17 and pop time was 20, then that would be in another component.
Exactly. Exactly. So, okay, so let's complete this one. So 4 is done. Next time instant is 5. So what has happened at 5? At 5 we have got push of E. So I have already popped C, right? So once I have popped C, I would come to B. So I have come to B now, and now I have to push E because at 5 time, next time is 5. I have reached 4. So next time is 5 and I am pushing E
Yes,
at 5.
so basically after pop C, now the top of the stack is B.
Correct, correct, exactly. Top of the stack is B, and you are simply you are not popping B, you are pushing E. So you had B, at the bottom of the stack you had A, on the top you had C. Now C is popped, so you have the top of stack B. Now B you are not popping because at 5 time instant you see you are pushing E. So E would be pushed on the top of the stack. That's it. And what is happening at 6 time instant? You see at 6 time instant we are popping E. So now E is again popped. Now what does it mean? When we are popping, DFS is popping means what? DFS did not have any other place to go from E. That's why it popped. Otherwise, it would, even if there would have been at least a single non-visited neighbor of E, then DFS would have gone to that neighbor, right? And we would be pushing something over here. So 6, let's say K, right? So you would put the pushing number as 6 and K would be pushed. But since there is no such K node where which is a neighbor of E and which has yet not been visited, that's why DFS had to pop it. Pop E.
No, there cannot be. I mean, pop time and push time cannot be same here. No, I mean if
No.
there is something.
I said if there is something, then 6 would not be the whole pop time of it. 6 would only
Oh,
be
okay,
the
okay.
push time of it.
Correct.
Okay. So here I have 6, and then again I would come back to 7. What is 7? Push time of D. Okay. So I have come to B. So again push time is 7 and D. Okay. And what is 8? At 8 I have pop of D. 8 I am again going back to B because I popped. So I have E, and then I have again pushed D, and then again I have popped D. And then I come back to B, and finally I see that B's pop time is 9. Okay. So I pop B from here, go back to A now. So B is popped finally. And I would go back to A, and I see the pop time of A is 10. So I would again pop it. Now, let's say if I have another data, push time of, let's say, Z is equal to 11. What does it mean? It means that see, push time 11 is there for Z. So if Z would have been connected with at least one edge with A, then I would have something like this. I would have some Z connected with A because DFS would travel to Z directly through A. But since there is no edge, since I can see that push time of Z is 11, right, which is out of the pop time of A, that is A is popped out, and after that Z is pushed in. That means I did not have at least a single edge to connect Z with A or any other node in this whole component. And that's why there is a separate vertex or a separate component over here, which is Z. And its push time is 11. Let's say there are no other vertices and that pop time is 12. So in this case, this is one component and this is one component. Two components would have been the answer, but we don't have anything like this. So the answer is 1. So this whole thing is a single graph. Okay. So refer the pre-post numbering lecture. It's the same thing.
So if it is asked what will be the top of stack at time 4?
At time 4, what would be the top of stack?
Yes.
So at time 4 means you have done the 4th operation. So what is the fourth operation? It is popping C, right? You are popping C here. Fourth. You are popping C. So C has been popped out, right? So what was just before C? These things are not yet there. We have just ABC was there, right? And time equal to 4, I have popped C. So this is obviously the top of your stack. B, right? In fact, that's the idea. You are returning back to B. And when B is popped, you are returning back to A. You will simply return back to the parent. You are at E. There are no other non-visited vertex. You return back to the parent, which is B. You are at D. Return back to the parent when you are no unvisited neighbor towards B. Okay.
So the
So-
return line is called something, right? I forgot the name.
Sorry, what?
The return arrow is has a different name also, right?
No. This is just an indication. This is not a return arrow. I mean, just.
Yeah, okay.
Back edge,
No.
forward edge. These are not the things.
Those are not these things. Those are separate things. Back edge and forward edge is simply like this. We have this push and pop time, right? Or the pre-numbering, post-numbering. So once you complete this pre-post numbering, I mean, in order to have this pre-post number, you need to run DFS at least once, right, on the graph. So once you run DFS on the graph and you have two dictionaries, right? You have two dictionaries, pre, okay, and post. Two dictionaries you created. You can check the code in the lecture by simply running DFS, and these dictionaries would store the pre-post for each of the vertices. Now, let's say what is forward edge? Forward edge is any edge which is a edge in the graph and which is also a edge in the tree, which is generated by BFS, this tree or DFS, whatever. Okay, so that is a forward edge, which is an edge which is there in the graph as well as in the tree. So that's why we call forward edges as tree edges also. Now, what is the condition with respect to pre-post for forward edge? The condition for forward edge is if I have an edge u, comma v, and if I have to decide whether it is a forward edge or not, then the condition is the pre of u and post of u, right? This ordered pair or this interval, okay, this must contain the pre of v, post of v. Contain. So if you see in our example, b to c, this edge, right? The pre of b is 2, the post of b is 9, pre of c is 3, and post of c is 4. So 3, 4 is contained inside 2, 9, right? 3, 4 is contained inside the interval 2, 9. And that's why I can say that the edge b to c is actually a forward edge or tree edge. Fine, but this is an indication. This is not an edge. I use those to explain that you come back to the previous period. Okay, so likewise for back edges, the condition is it would be just swap. So pre post of v would contain, the pre v and post v would contain pre u and post v. So that is the condition for back edge. And all those back edges, if you remove from your graph, then what you get is a directed acyclic graph, because back edges are basically creating the cycle. So in a directed graph, if you have back edges, right? So back edges will create cycles. So simply after you run a DFS and have these pre-post values, then you simply travel through all the edges of the graph again. And for each of the edges, you check whether the pre-v post-v condition for back edge is satisfying for that particular edge or not. Apply the condition on every edge and check whether it is a back edge or not. If it is a back edge, simply remove that edge from the graph. You repeat this process, obviously, since you are traversing through all the edges again and applying the pre-post condition to check whether it is a back edge or not. So again, it would take order of e plus b time. Basically, order of e time, order of edges time. Fine. So if you do that process after running DFS, which is after running DFS, which is again order of E plus B. So you had run 2 times order of E plus B, which is essentially order of E plus B according to asymptotic complexity. So that would give you all the back edges, and back edges, if you delete that, that is order of 1 operation. So you get a DAG. So from a graph, in order to construct an acyclic graph or directed acyclic graph, only thing is you need to find the back edges and remove them. How to find the back edges? Run DFS and get the pre-post numbering. Simply travel through all the edges again and check whether that particular edge is a back edge or not. If it is, delete that. You would get a, after you end the same process on all the graph, you would get a, on all the edges, you would get a directed acyclic graph. On that directed acyclic graph, now you can apply topological sorting and all other algorithms. Fine. So that was the summary for back edges and forward edges. Another one edge is there, which is cross edge. I'm just not explaining in detail, just moving forward, because those things are well explained in the corresponding live session. If you want in detail, please refer those live sessions. And cross edge is something where the condition is not containing anything. So in forward edge, pre-U post U must contain pre-V post V. In backward edge, it's pre-V post V must contain pre-U post V. In a cross edge, none of them would contain any one of them. So it would be a disjoint pair, disjoint set of intervals. Okay. And again, so the physical meaning, you don't have to memorize this thing that pre-V should contain post V. To understand the logic, this is very intuitive. I mean, it's automatically come. Okay, so this is trivial. This would always happen. But in order to understand that, you have to understand the logic. Please refer the live sessions of these weeks where we have understand where we have discussed the intuition behind these numbers.
Sir, what is the application of acyclic graph?
How can you? So in order to, let's say the prerequisite thing, directed acyclic graph. So you have to have the longest path algorithm. Wherever longest path algorithm is applicable, you have to apply it on a DAG. So let's say if I say that in order to do the PDSA course, you have to you must have done the Python course as well as the CT course. Okay, but you need not do the mathematics 1 or mathematics 2 course. Okay. Right? So it's simply represented in the form of a requisite graph, right? DAG. So if PDSA is a node, right? It would have a like thing like CT. And again, it's a Python. But again, I would have 2 other nodes. Let's say maths 1, it has no dependency on PDS. But let's say maths 1 has dependency on CT has dependency on maths 1. So I would have a graph like this. Yeah. So ultimately, in order to do PDSA, you must have done maths 1 at some time. Yeah. Right? Because if you do maths 1, then only you can do CT, and if you do CT, then only you can do PDS. So this is simply a directed acyclic graph. Why acyclic? What would happen if you have a cycle? Because there is no cycle in this. Yeah, but if you have a cycle, what would happen? In order to do CT, you must have done PDSA because this edge is there. In order to do PDSA, you must have done CT because this edge is there. So this is a cycle, right? So that is illogical. Yeah. That would never be possible. So these kind of dependency oriented problems where you have dependencies at different levels and you need to follow the proper dependencies, and then only you can actually complete the process. Those type of graphs we always have to use directed acyclic graphs, and in order to create directed acyclic graph, you can use the pre-post numbering to convert a normal cyclic graph into DAG. Fine, by simply removing the back edges. And that also is doable in order of E plus B time. Okay, pre-post numbering. Next question. So this I think is asking you for the correct condition for cross edge, right? Which of the following options are true regarding pre and post numbering used in the DFS algorithm on the graph? Okay, fine. Let's see. If UV is an edge of the graph such that pre-U post U contains pre-V post V, then the graph is necessarily cyclic. So what is this condition mean? Pre-U post U contains pre-V post V. Which kind of edge is it talking about?
Forward edge.
Forward edge.
Forward edges are cyclic or not? I mean, do they create cycle or not?
No.
No,
Only back edge too.
back edge.
So option A is obviously a wrong answer. It's not necessarily, it's not about necessarily, it's never a cycle. If all the edges are forward. Okay, so in a DAG, it would always be forward edge or cross edge. No back edges would be. Okay, so the next point is if UV is an edge of the graph such that pre-V post P contains pre-U post P. Now this is a back edge condition. Then the graph is necessarily cyclic. Yeah, that's correct. If UV is a graph and pre-V are disjoint, so this is the condition for cross edge. Then the graph is necessarily cyclic. Again, wrong because cross edges do not create cycle in directed. Let me just ask one question. Okay, so this is not a cycle because you see that there is the direction and obviously it's not a cycle. I have this edge A to C in the opposite direction. Fine. Now, if I run BFS tree on this and I get a BFS, I start BFS from A, sorry, DFS from A, and let's say I have this thing A, then I got an I traverse along this path to B. So A is my push time, B is the second push time, and again I have this edge over here. So C is my third push time. After that, everything is done. So 4 pop time, 5 pop time, 6 pop time. So this is my DFS tree. Now let's assume. Now let's see what happens. Let us check this edge AC. Okay. So is this a forward edge or not?
Yes, it is a forward.
Let us check DC. Is it a forward edge or not?
Yes.
Yes.
And AB is again a forward edge. So all three edges are forward edge. So you see that this is not a cycle because all these three are forward edges. And obviously we can see that because the directions are not aligned in the form of a cycle. Right? Now my question is, can you apply DFS pre-post numbering, not normal DFS, along with this pre-post numbering or push-pop numbering, whatever you want to call it, on undirected graph? Will it be able to tell you the cycles by simply using pre-post numbering? What would happen? See, if it's an undirected graph, then this is a cycle, right?
There will be cycle in if it is undirected graph.
Yeah, so if this is an undirected graph, then that means this is obviously a cycle. This is a cycle. It's an undirected graph, it is a cycle. But my BFS would be same, right? I would travel A to B, B to C, right? Because I started my DFS from A. So my tree would be same. And I would apply my forward edge back edge process condition and it would satisfy and tell, okay, all the edges are forward edges. And that's why it's not a cycle. But undirected graph it is, and therefore it is cyclic. So,
sorry to interrupt.
No.
In case of undirected graph, even if there are two vertices and one edge connecting them, then also it will be a cycle because A is connecting B and B is connecting A.
Yeah. There is no direction. If it's a closed figure, it's a cycle. That's it. Fine. It's a cycle. This is a cycle. Any polygon is a cycle.
I mean, a line is also a cycle in that case.
No, line is not a cycle.
Because A and B and B and A both are.
We don't consider it like that.
Okay.
At least you should have three lines to form a cycle.
Okay.
I mean, that's a triangle. Fine.
Yeah.
Okay. So basically, my motive was if you apply pre-post numbering on an undirected graph, it would give you wrong result. But actually, you do not have to go into the complexity of this pre-post numbering. Simply checking cycles are there in an undirected graph or not. You can do that with simple DFS and PFS. Any one of them you can do, just adding one single line of condition along with the visited thing, where you check if visited not equal to true. Along with that, you have to just add one line. Not one line, one in the same if statement, you have to add one condition. I will not tell that condition, and that's not in the exam also, but you should think about it. What is the condition? And if you can come up with something and post it on Discord, then we would discuss and maybe give the answer over there. Okay, so simply using a single condition and ended with the if visited not equal to true in DFS or BFS can give you the correct result whether a graph is a cycle or not if it is an undirected graph. Okay, so that is actually the first stage. Undirected graph checking was able to, we could do that by simply adding that condition. But since directed graph came, we could not do that by using that condition, and that's why we had to come to the pre-post number. Okay, oh, so that's it. So it's done. We have finished over here. So let me ask this. So week 5, the last week is left. I would discuss that now. Since there are 16 students now, what should we discuss it now or should we discuss it in the next session? What should we do?
We can do in next session, sir.
Okay, anyone else? What do you all feel?
But will you come, sir? It should not be some other person. Will you continue?
Okay, so I would at least continue the 5th week that I can see. So as of now, the planning is up to week 5 I would do, and then again I would continue from week 9, 10, 11.
Okay.
Okay, so 5 part I would do, then maybe Atul Bhaiya would start.
Okay.
And if there is something, I mean, any specific question or any specific topic that you want me to describe or discuss, you please tag me on Discord and mention the topic. I would reply. Okay.
Yeah, we need the last 4. One question is that question has weightage like last 4. Focus will be on last 4 weeks like that. Then we really need your help in the last 4 week discussion.
Last 4 week I would on Friday I would discuss. And regarding the weightage, would be proportionately. There is nothing more or less, something like that. It is. Okay. I would discuss on Friday. I would do the last 4 weeks. Only week 6, 7, and 8. These 3 weeks would be done by. Okay. Maybe since I would be anyway joining the session doing the 5th week.
Yeah, that will also be.
I would try to be throughout the session.
Okay.
Anyway, so better is you post it on Discord and tag me any topic. So I would discuss that. Only 9, 10, 11 anyway. Those 3 weeks I would do on Friday. Fine. And 5th week also I would do tomorrow.
Yes, sir. 5th week. Actually, I could not find it easy.
Okay, no issues. We would do that.
Okay.
Fine. So that is done. But before going to the 5th week, so this is a question that I want to ask, and please don't search the answer on the web. Try to think on your own. So this is regarding the Dijkstra algorithm only. We would discuss all those things again tomorrow. But this is one question on Dijkstra. The question is, so if I simply add equal weight to all the edges in a graph, there is a directed graph on which I would apply Dijkstra to find the minimum distance between all the vertices from a start vertex. Now the question is, if I simply, let's say I got a path, right? I applied Dijkstra, and after applying Dijkstra, I got a shortest path between, say, let's say my start node was A and my ending node was T. So my shortest path length was, let's say, K units from A to T. This is given to me by the Dijkstra algorithm. Okay. Now what I do is modify the graph by simply adding equal weight. This is very important. Equal weight and adding. I'm not substituting. I'm adding equal weight to all edges. So let there be whatever number of edges are there. To all the edges, I am adding, let's say, two amount of weight, plus 2, plus 2, plus 2, plus 2 to all the edges. The question is how many times the path from A to T would change. Not how many times, I mean by how much amount. And I mean, that is still the shortest path. I mean, would it change the shortest path, or I mean, since we are adding to all the edges equally?
No,
so,
it wouldn't.
It won't change the shortest path.
Okay, so what is the? I mean, how many of you want to say that it would change? Please tell. I mean, acknowledge that by raising your hand. How many of you think that it would change? The path would change.
Sir, can you repeat?
It's equal weight, so it won't change, right?
I mean, I don't know. I'm just asking you. So, yeah, the question is, Dijkstra is applied. I got a path. The weight of that path is k units. So, from A to T, A is the start node, T is the destination node. The path is k units. Now, that's the shortest path by applying Dijkstra. And there is no negative edge. All those things are not there. Simple graph. Now, I am adding equal amount of weight to all the edges of the graph. Let's say I add 5, I add 5 to all the edges. I add 10, I add 10 to all the edges. Will my path change?
No.
If it, okay, great. If it does not change, by how much amount? I mean, my path remains same, but obviously it would increase its weight, right? Because I've added some value to all the edges. So how
Yeah,
would
just
2 into n minus 1.
n minus 1, right? N minus 1.
2 into n minus
2k.
If I add 2, then it would be 2 into n minus 1.
Yeah.
Yeah, that is, yeah, k into n minus 1.
See this.
It might change. Suppose there is a we were earlier circumventing one edge by two edges for which the
Okay.
cost were
Exactly. Great.
coming less than the single edge.
Exactly.
But if the difference between the single edge and the double edge were not that much, which were offsetted by this 2D and D factor, then the graph will, I mean, the path will change.
Exactly. See, thanks for that. And yeah, the answer is the path might change. And what is the simple scenario? I have a path like this, which I have taken. Right? This is one node. This is another node. Okay. So, and I have another path over here like this. This is A, this is B. Fine. Let's say this is 10, this is 5, this is 20. Okay. And let's say this is, so how much is the path? 20, 30, 35, right? So let's say this is 35, this is 5. Obviously it is 40, correct? So this is longer, so this path is longer. I do not take that. This is my shortest path given to me by Dijkstra. Now I am adding, let's say 5 to all the paths, right? I am adding 5, not 5, let's say I add 10 to all the paths. Okay, so I add 10 over here, 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 I add 10 over here. What's happening then? What is the length of this upper path? It is 20 plus 15 plus 30.
65.
What is the length of this path?
60.
Okay. 15. Now if you run Dijkstra, you will get this path as well. So why did it happen? As exactly the point.
Number of edges.
Exactly. So if you have more edges in a path, even if the edge weights are same, sorry, I mean you pick the path which the shortest path, right? You pick the shortest path because even if it had more edges, even if it had more halts means you have to go to multiple vertices in order to reach the destination, right? So if there are more edges, but the weight of all those edges were small, and that's why it is the smallest path, the sum of weight of all those edges. And let's say there is another path to the same destination vertex from the source vertex, which uses very less number of edges, but the edge weights are quite large. And that's why the sum of the edge weights is giving you a larger value, and that's not the solution. That's why Dijkstra is a solution. But when I'm adding a constant value to all the edges, the illusion in this question is we all think that we are adding a constant value, so why it would matter? But the problem is your path has more edges. If your path has more edges, then I am adding on edges. I am not adding on weight basis. I am adding on edge basis. So if the path has more number of edges, you are essentially adding more weight to that path. Because if there are n edges, you are adding 10n, right? But if the other path which was there only with 1 or 2 edges, even if that single weight of that edge was high, but you would only add 10 one time. Because it's a single edge connectivity, or let's say at least a two edge connectivity. So you would add 10 two times. And that's how, even if the edge weights were more initially, after adding the value, right, some constant value, it would change. It might change if your number of edges are less in the path. So that's the observation. Yeah.
And if like other customers mentioned, like the difference between the weight of the initial graph should be like less than the increase, right?
Exactly. So I said that I would not add 5. If I would have added 5, what would have happened? I added 10. What would have happened if I have added 5? So it would be 50. And in that case, it would be 15, 10, 25, and 50. See, if I would have added 5, what would have been the result? It would be 10 plus 5.
Yeah, it would be equal.
It would be equal. Right? It would be equal. So what happened over here? It would be equal. Why? Because if I add 5, right, how much more was this path? How much more was this path than this path by 5, right? It was 40 and it was, it was 40, it was 35. Upper path was 35, lower path was 40. Correct? So I was more by 5. And how many edges are there? In the lower path, I have 2 edges. In the upper path, I have 3 edges. So if I add 5, so in the upper part, I would add 5 3 times. So 3 into 5, 15 is the net increase from the initial value in the upper part. And net increase over here is what? How much? 10. Because 2 edges are there. 2 into 5, 10 is the net increase after adding 5. So 10, but initially itself I was more 5, right? The lower path was more by 5, amount 5. So the net increase in value is actually 10 plus 5 for the lower path, which is 15. And that is actually substantiated by this one extra edge. So it is 15 and 15, both places. So that's why you got the answer as 15 both the places, if I would have added 5. So the idea is, there should be at some point, depending upon the number of edges and the weight that you are adding, you have to decide that whether it would increase or decrease, whether the path would change or not change. But if the question is asking you, whether is it possible that the path might change after adding a constant value to all the edges, definitely it's possible. Because if the path which is the least path has multiple edges and lots of edges, then the constant that we are adding, that gets added multiple times compared to a path which was quite heavy, but at least it had less number of edges. And that's why in the new value, new graph, everything might change. And maybe the path which you did not take earlier, the heavy path, now is becoming the lighter path. Right?
So if the options or path always change and path does not change, so that is a wrong options, right? Always, if it has
always change is also wrong, does not change is also wrong. It might change.
Okay.
Okay, but the main trick is same weight. That's why actually I underlined the equal word 3 times so as to mislead all of you. That it doesn't matter whether you add it. Actually, since you are adding equal weights, that's why it is making the path different. If you would have added different weight, then we could not say anything, right? So if you add equal weight, then depending upon the number of edges, it would change. Okay, so there is another one interesting question regarding Dijkstra that I will discuss the next day. because it is based on that negative cycle thing we would discuss. Fine. Okay. Thanks. We would do tomorrow session, week 5 at least I would do, and then. Thanks a lot.
Sir,
Yeah, you
this
want to
paper,
ask something? Anyone wants to ask something, they can ask.
sir, exactly one doubt. So, like this paper is uploaded on the portal. The question, like
No,
all the
no,
question.
no, it's not uploaded. Should I upload it? Okay,
Yeah,
you can
it's
check on the YouTube itself. No, now it is in the recording.
Yeah, I know that it is recording. Only I just want the question, just a quick revision for that.
No issues. We would upload it. Okay, thank you.
Thank you, sir.
Hello, sir.
Yeah.
Sir, I have a doubt in graded 2, question number 2.
Which graded, which week? 2?
Week 2, yes, question number 2. There is a questions based on the order.
Just a second. Graded week 2, question number 2, 1.
It is given that.
Okay, so this one, right? Just a second, I'm sharing.
Yes,
Yeah.
this one.
Yeah. Yeah, you want to ask something specific?
Yes, question number 2. Yes, actually, sir, how we approach these questions?
Okay, so let B and A and W and with best case, average case, and worst case time of running time of an algorithm. Okay, executed on an input size n. Okay, which of the following either are true? Okay, so an is what? Average time. So order of Bn, order is what? Order means it is the, so first of all you upper bound, correct. So if I'm writing order Bn, that means Bn must be upper bound of, no, order Bn means Bn is the upper bound. Bn is at the top, An is below it. If you draw the graph, so
okay, yes.
Okay. So that's the definition. So in the scratchpad we discussed that, right? So if this is my time and this is my input size n, right? So if I have a graph like this and a graph, let's say like this, right? Then if this is Fn,
this is the order of Fn.
So I would write G of n
is O of Fn. Yes.
Fine. So inside the order, whatever you would write, that should be the upper one.
Upper bound. Yes, I'm little bit confused about that. How?
Going to that. So if that is the scenario, I know O of Bn means Bn must be the upper bound of A. That is, B should be at the top of A. Right? Now, what is B? B is the best case time.
Yes.
Correct. So B means if it is the best case time, that is, it takes lesser time. That is, its value is lower. Best case means what? Okay, let me just go over here again. Sorry. Best case means what?
It should take the lower time.
Okay. Sorry. I just did one thing wrong. It should be the opposite. N increases, time goes over there. Okay, I'm doing it in this manner only. Function of it. Okay, so best case means what? That is, I mean, it would take lesser time, right? So this would be something at the bottom. I mean, best means better performance. Better means it takes lesser time. Lesser means it should be in the y direction. It should be at the top or it should be at the bottom.
It should be a bottom for the increasing.
Bottom. Exactly. If it is best means it is taking lesser time. Less means towards the bottom of the time axis, right? So it would be towards this bottom area. So anything which is at the bottom, that is the best case. Anything which is at the top, that is the worst case, because that is taking most time. Now, if I have the best case, B of n, and I have the average case was there, right? Now what was that?
Average case.
Average case was there, right? So let's say in my example, let's go back to the graph which we had over here only. Yes, if these are not fn bn, let's define it exactly like this. So this is my worst case, which is actually worst case wn. Then I have average case p of n, and then somehow I have this best case b of n. Okay. Now order means it should be at the top. And if I write this statement, what was the statement? A of n equal to order of b of n, right? A of n equal to order of b of n. Is that means according to this statement, since I am writing b of n inside order, that means b of n must be upper bound. I mean, it should be at the top of a of n. Is it so in the graph? No, right? B of n is at the bottom. Why? Because it is the best case. It should be taking less time. So it is located towards the lower part of the time axis. After that, average case, a bit higher part of the time axis. And then at the worst case, which is at the topmost part of the time axis. Now you just think, just draw this diagram and then simply put the values. Order of Bn, no, wrong, never, because BNS is at the bottom of A of n, right? But the opposite is true. If I write B of n equal to order of A of n, that is correct. Because why? A of n should be top of B of n, correct? A of n is at the top. You just simply draw this and simply apply, you would get the answers. So let's take another example for your just a second. Yeah, let's take any other one. Let's take this one. Okay, now omega of n means the best case. It should be bounded at the lower end. Okay, so order means it should be upper end or upper bound. Omega means best case, which is lower bound. So if I write a of n omega of b of n, that means what?
It should be below the bn.
I have a of n omega of b of n. Okay, so that means b of n, since now I have used omega, that means b of n must be at the bottom, a of n must be at the top, according to this statement. B of n should be at the bottom, a of n should be at the top. Okay, because this is the best case, this is the lower bound. Okay, if this would have been the upper bound, B of n should be at the top, A of n should be at the middle. Okay, so drawing this diagram was the first thing. See, forget about all the statements that were given over there. It was told that AN is the average case, BN is the best case, WN is the worst case. Worst means it would take more time. Accordingly, we have drawn it at the top of the time axis. And then A and then B. So this is your first step, that's done. After that, you have to check the statements, which of the statements are correct. So the process is you write the statement. So here I have written the statement. And then you interpret that statement and check whether that is the case in the graph that you have drawn, this graph. If that case is matching, then you say it is a correct statement, otherwise you say it is a wrong statement. So in this case, what would happen? A of n is omega of B of n. Definition of omega means that your B of n should be at the bottom, A of n should be at the top, because B of n is the best case. Okay. So is it same in the graph? B of n is it at the bottom and A of n is at the top? I mean, top means above B of n. Yeah, that is actually the case. A of n is actually above B of n, B of n is at the bottom. So this is a valid statement. Got the point?
Yes, sir. Now, yeah, I got it.
Sure.
So this statement says An is a, I mean, omega of Bn means Bn being the bottommost part. So An is the worst case than Bn, correct?
An is worst case than Bn, correct. So if I write Bn equal to order of An, that is a correct statement.
Yes, but then An equal to omega of Bn. So is that correct?
An equal to omega of Bn, yeah. Because omega means best case. Best case means lower bound.
Yes. So, okay, the lower bound of An is Bn. That is what your statement says.
Yeah. That is the definition of omega. So definition of, so if I write order of Gn equal to f of n, what is the f of n? The definition is what? definition of order is C into G of n must be greater than f of n. What is the definition of omega? If I write omega of G of n equal to f of n, that simply reverses it. That means C into G of n must be lesser than f of n. So that means what? G of n is smaller in time than f of n. So G of n is a better case than f of n. In other words, it is the best case considering f of n. Okay? Yeah. Yeah, any other doubts?
And what is the symbol of average case we write?
Average case
any
is
symbol we have for average case?
We have theta. I think it's not discussed in the course. We generally represent it with theta. Theta, omega, and phi. Not phi, sorry. Big O. Average case is theta. Condition for average case is, see, if I write theta of G of n equal to f of n, that means some constant C1 into G of n must be greater than f of n. Right? This is the condition for which one? This condition, see? The condition for big O. And on the same line, I would add some other constant into G of n, like this, which is the condition for omega. So for omega and big O, the averaging, I am putting f of n in between them. This is the condition for omega. This is the condition for big O. And fn is in between them, so that's why we call it average. Right? So in terms of graph, if I draw, so you have the same x and time axis like this.
Graph is okay. No, I mean, if we wanted to write in that expression term, how we can write for theta?
This is the expression for theta.
You know, like an equal to omega bn kind of thing. Can we write for theta also?
Yeah. You can write. You can write for theta is, I mean, so you actually in theta we don't use like that because you are bounding something by upper and lower bound. That is what is used, upper bound and lower bound, and that's why you use omega and big O. Theta is mostly used to represent not like theta of f of n equal to theta of G of n. We generally don't write, but mostly even if it is written, it generally means that algorithm would always give the f of n function as the growth function, irrespective of the input. For example, we have learned one such algorithm. We would write the complexity of merge sort as theta of n. I mean, since we have not written, I mean, we have not learned the theta definition or something like that. That's why we have not used it. But if you want to be very theoretically correct about mentioning complexity, and if you mention the complexity of merge sort is order of n log n, right? It's a correct statement, but it's not a complete statement. If you write the complexity of merge sort is like this, n log n, again it is a correct statement, but not a complete statement. But if you write this, then it means a complete statement. So it is mostly used like this. Because merge sort will always give you n log n time. And if you want to bound something, like you put some function equal to theta of some other function, that is not generally done. Not generally done. At least I have not seen. I have not seen that. Okay, it might be there. You might check that on the web or in some good book.
So like if it is theta of n, that means that if we have theta of n, that means that we have like is that what we call a optimal algorithms?
Yeah, if it is a theta of n, that means your best case is also n and your worst case is also n. That means your algorithm, irrespective of the input, it always takes order n time. Like merge sort takes, irrespective of the input, it takes n log n time. So we can call it theta of n log. But okay, don't confuse yourself with this theta n and all those things. These things are not there and not required for coding related purposes. These are more towards academic point of view. So yeah, we would be ignoring all those things. Any conceptual doubts if you have, please ask. Because sir also discourages discussing all these theoretical topics. So yeah, let it be there. Any other doubt regarding the normal complexity?
Sir, general doubt. Sir, how is the means? I mean, week 10 and week 11. It is week 11 is linear programming, and it is some mathematical concept on this.
Yeah.
So, is it important in the perspective of the quiz?
You would not be asked to solve mathematical problems, but obviously you would be asked to interpret the problem statement in terms of the linear equations.
Okay.
Getting the point? So you have to read the comprehension or a story.
Okay.
I mean,
okay.
sir has also not solved it. Did sir solve the simplest method? No, right? Sir simply just explained.
No, but graded. I think in graded, I think there is some
graded
question.
one question was there. Graded one question was there. That also you can solve it by simple mathematics only. You just put the values, check the vertices, and that's it. It's not that difficult. But I mean, the maximum point.
It has come in a previous
it would not be asked, that we can say.
Okay, okay.
But interpretation would be there. You have to understand how to interpret a comprehension into the linear equations.
Yes, these things I know, but if
yeah,
yes,
so
these
solving
things I know.
Solving we are not planning to.
Okay, okay, sir. Thank you.
So next two sessions are planned for 8 p.m. or the same time, because this.
I think it is one is from 8 because Friday I would be taking, and Friday
next both are at 8 to 10.
Both are 8 to 10, right? Friday 8 to 10. I mean, we have to be doing it from 8 to 10.
Can it be earlier? Just
I understand, but sorry, because those 3 weeks actually I would be taking, and I would be actually in the institute for a work till 6:30 or 7 o'clock.
okay, no problem. Sure.
Anyways, I would finish the topics, and yeah, then maybe you can see the recordings. If you have any doubt, maybe post it on discourse, right? Any questions regarding the 3 weeks that you want to be discussed particularly, right? If you are not able to stay for long on Friday, it's better you post such question on discourse itself, and also mention that it's okay if you discuss it in live session, right? Because if many of you mention many questions, it would be difficult for us to answer within a day. But just mention that it's okay if you mention it in live session, then we will discuss those questions in the live session. If you cannot stay for long on Friday, and if you have some questions to be asked, so we will discuss those questions, and maybe you can see it on the YouTube later.
No, sir, we'll stay. I don't.
Thanks. Any other thing? Any other doubts?
No, sir. Thank you.
Great.
Thank you very much.
Thank you.
Thank you, sir.
Thank you.